All right, hello everyone. Welcome to the second day of this climate variability change and Earth system prediction now. So we're having a joint session to begin with 5 talks between climate variability and change and Earth system prediction on ENSO and its predictability. A reminder, this is the code of conduct, so please be respectful and constructive in your feedback. And then here's just the schedule for the day. So like I said, we have a joint session between climate variability and change and Earth system prediction. And then we have a number of talks on subseasonal to seasonal timescales and then decadal timescales. And then there'll be a discussion for the Earth system prediction working group at the end. So we're going to kick things off with an in-person talk by Nathan Lenson on mechanisms of multi-year ENSO predictability.
Super, thanks, Isla.
I'll give you 12 minutes.
Great, thanks. Yeah, thanks to everyone for making it up the hill and online. I'm going to be talking today about some work I've been doing over the past few years in my PhD at the IRI with Lisa Goddard and others, and now at CU Boulder with Pedro Dinezio. And I wanted to recognize all the other people who have helped me along the way through discussions. Sorry about the feedback. All right. So I'm going to hop right into my basically my main result, explain this, and then talk through some of the interesting features and curiosities on this figure. And so what I've done here is run perfect model ENSO predictions in CESM1 using the model analog technique of Hui Jing, Matt Newman, and et al. And what's exciting about this is we're seeing significant event detection skill out to 3 years in this perfect model setting. So this is not necessarily a new result. We've seen perfect model ENSO skill at leads that long. But this is exciting for a few reasons. One, it uses a method that is incredibly computationally cheap, which I'll get into a little bit more in a bit. And two, it allows us to do some really cool experiments because we're able to run a bunch of different experiments on our laptops and think about them. And so I'm going to be talking about this ROC, area under curve scale, as my primary skill metric throughout this talk. It's an event detection skill and a probabilistic event detection skill, meaning it's scoring forecasts on how well they issue probabilistic forecasts of El Nino, neutral, and La Nina. And so a score of 0 is equivalent to climatology, and it maxes out at 0.5, a perfect skill forecast. And so again, here we're seeing that we have positive scale in predicting the state of El Nino or of ENSO all the way out to 36 months, as shown by the dots, showing significant scale at each of those leads. And so really the motivating question is not just that we can get this scale in a perfect model setting, but trying to understand what sort of mechanisms or dynamics enable significant ENSO scale at leads of 2 or greater years. And so there's been a lot of work over the past few years in trying to understand these potentially predictable multi-year ENSO events, particularly up here at NCAR in this working group. And so we have kind of 3 classes of events that we think we might be able to get longer skill on just because of how the ENSO system generally evolves. And so the first one of these sequences of events is been well known since the 80s. Put the recharge oscillator paper up there, but many people have written about this, that La Nina usually follows El Nino. So if we're sitting in the middle of a big El Nino, we probably have about a free 12-month forecast of La Nina coming the next winter. More recently, Dinezio and Wu and others have spent a lot of time looking at other sorts of sequences of events and durations of ENSO events, and have shown that large El Ninos generally lead to double La Ninas. And so that's another chance of getting a few-year predictability. If we're sitting in the middle of a large El Nino, we might be able to actually get a pretty reasonable 24-month forecasts then. And then the third one that's been written about more recently by Jian is that a later onset of El Nino leads to an increased chance of a second-year El Nino. So again, then we might be able to get a 12 to 18-month lead forecast at higher skill than a lot of other times. And so the idea here is to use these model analog perfect forecasts to explore the predictability of some of these classes of events and see how much they could be contributing to this high scale at 12, 18, and 24 months. And so here we're going to be using the model analog forecasts. I'm going to give a brief introduction, which might be useful for the rest of this session as well. And so the idea here is really simple. It comes from some work of Lorenz and doing some weather forecasting back in the early days. And the idea is you have an observed state of the global ocean or the tropical ocean or the Indo-Pacific Ocean as in this case. And you look through some library of data and find the closest match in that library of data to the current observed state. And the idea is if you pick a reasonable way to match and you match on fields of interest, that those states in your data library will evolve similarly to the real dynamical system. And so then all you have to do is take those states in your library, your analogs, and advance them forward in time to get a forecast. And so here I'm going to be using, just Indo-Pacific sea surface temperature and sea surface height following the original Ding papers. And just to highlight, probably everyone in this room has seen these results by now, but just to highlight that these forecasts are doing a really reasonable job up with the state-of-the-art of forecasts. On the top row, we have the NNME 6-month anomaly correlation for SST and precip, and on the bottom we have the analogs, and if I had removed the labels, it'd be pretty hard to tell the difference between these two forecast skills. Oh, yeah. Yeah. They all say analog.
They're both analog.
They're both analogs. I grabbed the wrong figures.
Is lower than the NNME.
Okay. I don't know if online could hear that. I had the author himself correcting me that these are all analogs and the NNME is a little lower than these. So just to motivate that these analogs are performing state-of-the-art forecasts, so we can be confident in using them to answer some more science questions. And so here I'm using analogs selected from 1,000 years of pre-industrial control and running forecasts on the remaining 800 years of the CESM 1.1 pre-industrial control. And like I said, this is really exciting from a science perspective and one with like a limited budget on Cheyenne, because I'm able to run all of these 800 years of hindcasts in 1 hour on my computer. And so we can start thinking about more ambitious experiments to do in the future. And so here I'm back to my this skill. So this is skill shown over all months, or excuse me, this is skill of DJF. And there were kind of two areas of interest I wanted to investigate in this study. First, we have the hypothesis that this 1 year larger La Nina skill over El Nino skill is partially driven by the predictability of El Nino into La Nina. And second, that 2 year La Nina skill is partially driven by predictability of strong El Nino into double La Ninas. And so what's really nice about being able to run 1,000 years of hindcasts is we're able to stratify our forecasts and reassess skill and have some sort of robustness in our results. And so here I'm showing the 12-month ROC skill again, looking at La Nina prediction, and I've stratified by the state of ENSO at initialization. So this first bar is showing our skill at forecasting La Ninas if we're initializing in no El Nino 12 months prior, and then a weak El Nino, and then a strong El Nino. And as expected, when we're, at least in CESM 1.1, when we're initializing in DJF in the middle of a strong El Nino, we're basically always gonna have a La Nina afterwards, and the forecast system picks up on that and gets nearly perfect skill, as shown by this bar being really close to 0.5. And so this is a pretty simple but like powerful way to check that a lot of, or at least a significant amount of this one-year La Nina scale is driven by the predictability of El Nino into La Nina. What's also cool about this large amount of sample size is we can do retrospective analyses as well. So here now I'm starting at a La Nina and looking at backwards. And so here is in blue, the composite of all La Nina events in this hindcast period. And as we can see on average, they're followed by some sort of El Nino event, and often quite a strong one. Or excuse me, preceded by. And so what we can do is look at 12-month forecasts then of this event and composite them. And so we can see, kind of lining up with our prospective analysis previously, that these most of the forecasts of these types of events are following the trajectory correctly, coming out of an El Nino into a La Nina. And as we look at longer leads, we can see how we do trying to predict that El Nino into the La Nina, and you can see that at 18 months, we're still doing quite a good job, but the uncertainty at the 0 lead at the actual La Nina event is increasing. And then by 2 years previous, the forecast model struggles somewhat, but still does a good job. And so an extension I'm thinking about here is trying to show that the forecasts that do detect this El Nino correctly will also get the La Nina correctly. And so then I extended out this stratification analysis to 24 months, hopefully to see that a strong El Nino would lead to good 2-year La Nina predictability because of the double La Nina that often follows a strong El Nino. And there's maybe some evidence for this, but when I was first making this figure, I expected to see this really strong red bar here, significantly higher than these 2 other ones. But I think more work needs to be done looking at this kind of 2-year La Nina predictability, because CESM 1.1 is another model that, like the real world, like we're experiencing right now, can go into multi-year La Ninas without an El Nino. So it looks like this bar is probably picking up some of that skill in predicting 2-year La Ninas not out of an El Nino potentially. So this is, I think, not exactly the result we were expecting, but opens up the door to thinking more about these multi-year La Nina events. And why I'm still pretty excited about the predictability of 2-year La Nina in this case is the retrospective analysis. So here's the composite 2-year La Nina event in this hindcast period, and it's really quite strong and robust, and in CESM1 has been written about considerably before. And we can see that our forecast does a pretty good job out of the first La Nina, forecasting the second La Nina. It really struggles, as you might expect, 18 months out, but it does an okay job at 2 years out. So I think just that there's still quite a shift below 0 in these 2-year retrospective composites, that there might be some further subsetting to understand how we're getting potential 2-year La Nina skill. And so some quick conclusions: that there is at least 3-year perfect model INSA skill in CESM1 using model analog forecasts. And this has been confirmed in quite a few other models at this point. I just left with CSM 1.1 to make this story a little simpler today. When we're able to make 800 or 1,000 years of hindcast, we're able to do some cool statistical things to really understand where our skill is coming from. And we were able to show that strong El Nino events really lead to predictable La Nina events, as we would hope. But we didn't really see the double La Nina predictability, at least in this more simple analysis. So it'll be interesting to continue to dig into that. And then I just showed the Nino 3.4 retrospective composites, but we'll also be able to composite entire fields out of the ocean and atmosphere using this technique. So it'll be really interesting to dive into some of the precursors of these 2-year La Ninas and understand if there's predictability there as well. And so, yeah, going forward, I'm going to be working on this spring and excited to talk to all of you about this as it moves along. But I'm really excited to compare model analog and initialized ENSO dynamics and predictability, because a lot of these model configurations were also included in the CMIP6 decadal prediction experiment. And also investigate the skill transitioning out of multiple La Nina events. Like if you've been following the news, some people are saying that we basically are already in an El Nino due to maybe some overconfident forecasts coming out right now. So I'm excited to to use these techniques to investigate some of that. So I'm happy to take any questions. Thank you.
Great, thanks. Yep, Matt?
It's a small question, which actually might be related to this. When you're picking your analogs, are you going based just on the SST anomalies, or are you using other variables?
Here I've been using sea surface temperature and sea surface height.
Okay.
For this, I've done also sea surface temperature and didn't see much difference. Sometimes that seems to matter. I saw in your preprint that you did a great analysis of that, so that was helpful to see when it might matter.
You're off the mic, by the way.
Oh.
I think he's off the mic.
They should hear us through the ceiling.
Anyway, well, okay, so, yeah, I mean, one thing you might try then is other, I mean, we use SSH because that's what you can get for real world, but in a perfect model, you could use other measures of heat content. It might be interesting to see if that's what you're not capturing with these double events.
Yeah, that'd be interesting. Also interested in some measure of some measure of westerly wind. This gets a little trickier to figure out how to aggregate that, but maybe sometime for the summer forecast could be interesting to try to include.
Yep, Laurent?
So there's a paper that's going to come out by Sullivan Tual and Boris Dewitt about this extension of the recharge oscillator, simple model by using, instead of a fixed SST index, they're using the worm pool index or a cold tongue index. So following on Matt's point, maybe using that as a metric in the analog could be actually quite nice. And what they show in their paper, that they're actually able to reproduce this double La Nina or multi-year La Nina thing with this very simple extension of the standard model, I would say. So that might be something to try.
That'd be neat. I'll follow up with you over lunch and get that from you. Thanks.
Okay, thank you very much.
Thanks,
So our next speaker is Dylan Amaya about future ENSO skill. Let's bring up your slides.
Test. Yeah, that's the one.
Okay.
Cool.
Make sure that it does.
Test. Good online? Yeah? Okay, sounds good. Hi, everybody. Thanks for fording the blizzard to get up here, and thanks for those online that joined us today. I changed my title a little bit. I am going to be thinking about future ENSO predictability, but I also want to think more broadly about climate predictability. I think this is a broader question. Happy to work on this project with a group of folks from NOAA, CERI, CU Boulder, and NCAR, so basically all of Boulder is involved, but really excited to be talking with you all today about this. When thinking about seasonal climate prediction, it's important to remember that ENSO is by far the main source of deterministic seasonal forecast skill for most things we care about, and this is just one way to illustrate that. This is taken from J. Cox et al. 2022, and it's a paper that looked at marine heat wave forecasts in seasonal forecasting systems. And this is just a time series showing the global average marine heat wave forecast skill at 3.5-month lead as a time series, where the shading of the color of the line is showing you the ONI index value at each time step. It's not really important you understand what the forecast skill metric is, but just higher values mean more skill. And basically what it's showing you is that you tend to get more forecast skill at 3-month lead when the ONI index is either strongly positive or strongly negative. So just indicating that you have a strong El Nino or a strong La Nina event. So just sort of hammering home these points that ENSO is really the main determining factor. And it's not just marine heat waves that this is true for, it's other things like precipitation, circulation, soil moisture, most things that we are trying to predict on seasonal timescales. And what's really interesting about that is that climate models project significant changes to ENSO and its teleconnections in the future, even if the nature or character of that change is pretty uncertain across models. For example, these are 5 large ensemble simulations showing you the Nino 3.4 standard deviation in 30-year running windows out into the future for boreal winter. And you can see that some models are increasing, some models are decreasing. CESM2 is doing this funny thing where there's a peak in Nino 3.4 variance in the mid-21st century, and MPI is showing basically no change in ENSO going into the future. But it's safe to say that if the character of ENSO were to change in the future, we might expect similar changes in our ability to predict the things that are most influenced by ENSO on seasonal timescales. So this is the overarching question that we're after today. And one way that we can address this issue is by using perfect model analogs. So thank you, Nathan, for the awesome introduction to the concept. I won't go into too much detail again about how model analogs work. I thought Nathan did a great job there. I'll just mention that our technique will be a little different in that Nathan was drawing analogs from a pre-industrial control simulation. Whereas we are going to be drawing analogs instead from large ensembles, which provide enough data to give you robust statistics about your forecast skill and predictability, but it also allows you to draw analogs from time-varying climate states that are affected by radiative forcing changes. So that's the goal today, is we're going to assess time-varying predictability using perfect model analogs from large ensembles, and we're going to look at changes in climate skill or predictability across time in these different climate states. So just very quickly about how this works. This is our workflow. We're going to be drawing model analogs from a large ensemble based on global maps of what I'm calling SSTA star, which, if you were at Clara's talk yesterday, is the same thing as ISST. It's just sea surface temperature anomalies with the ensemble mean from each ensemble member removed. And we're going to do these in consecutive 30-year periods. So for example, 1921 to 1950, or you can go all the way to the future, 2071 to 2100. Having done that, within a given large ensemble, we're going to take turns treating each ensemble member as the truth, or as our observations, and we're going to draw analogs from the remaining ensemble members. So, for example, in CSM1, you might want to want to find analogs for January of 1944 in the first ensemble member. You can find your 10 best analogs from the other remaining ensemble members from a library that includes all of the Januaries from across all of the ensemble members. And in this case, we're able to get 10 good matches on a global scale, and these are our forecasts. So for CSM1 as an example, we end up with 40 climate ensemble members, 10 forecast members for 12 months in a 30-year period, so we end up with 144,000 forecasts to play with in a 30-year chunk. So lots of good data. And we can repeat this cycle for different 30-year periods, look at the prediction skill in the past, look at it in the future, take their difference, and see how predictability may change for a variety of things that we think we care about. So we're going to do this in 5 single model initial condition large ensembles, so CSM1, CSM2, GFDL SPEAR, GFDL ESM2M, and MPI. These 5 models were chosen for a couple reasons. One, all of their ENSOs are decent. They all have different biases for different reasons, but they're doing something reasonable. Also, they all have different trends as what they think ENSO is going to do in the future as far as its variance goes. And they all sort of sample, the different outcomes that we might expect, whether that's an increase, a decrease, or stays the same. So thanks to Nicola, all of these models have been regridded on a common 2.5 by 2.5 degree grid from 1920 to 2100. And we're going to be assessing predictability using forecast skill based on anomaly correlation coefficient as a function of initialization month and lead time. So just for the sake of time, I'm only going to focus, or not only, but I'm mostly going to focus on the results from CSM1 today. So take note that CSM1 in the future, Nino 3.4 variability increases. So let's look at some of the results here. This is global forecast skill across the ensemble mean of CSM1 at 0-month lead from 1921 to 1950. So this is just telling you how good of a match your analog is at initialization relative to the thing you're trying to match. And overall, you can see that there is high skill for most of the globe. And I should mention that this is the correlation for all months, and we'll break it down into seasons here in a second. But overall, the analogs are doing something reasonable, and they have high skill, similar to what Nathan had shown from the Ding et al. Papers. But you can extend this out to 24 months, and you can see that as you go out, your forecast skill decreases as you would expect, but you still have some significant skill in the tropics associated with that 2-month INSO forecasting skill that Nathan was highlighting before. But the cool thing is you can play this game again for a future period, 2071 to 2100, and you can take the difference between these two periods and look at the change in predictability of global sea surface temperatures in this model. And in this case, sea surface temperature forecast skill increases nearly everywhere, particularly at long leads and particularly in the tropics. You can see that El Nino-like signature. And you can also see places light up that are typically influenced by ENSO, things like the tropical Atlantic and the tropical Indian Ocean. But it's not just sea surface temperature that we can look at. Even though we're drawing analogs out through sea surface temperature, the cool thing about the analog technique is that you're just using sea surface temperature as a way to pick a climate state that looks like today. And once you pick that climate state, you can look at all the variables that you're interested in and follow their trajectory as forecasts. So we can start to look at things like surface air temperature. This is showing you the change in forecast scale between the late period and the early period for surface air temperature, where over the ocean it's just SST, but over land it's 2-meter air temperature. And you can start to see some significant changes in predictability for air temperature over land. And you can do the same game for precipitation and 500 millibar heights. So there's a lot to unpack here. Again, this is all for CSM1 and for all months. But maybe I'll just focus our attention on a couple features. One, you can see that regardless of variable, you increase your forecast skill, again, particularly at long leads in the tropics. But you can also see some remote impacts of INSO that may show some increase in predictability as well. For example, if you focus on the US West Coast, you see an increase in forecast skill along the American Southwest, both for surface air temperature and precipitation. And you can also see the Aleutian Low and the Azores High light up in the Northern Hemisphere along the path that the PNA would take. So in this case, it suggests that predictability is increasing for remote INSO impacts, at least in this model. So this is the predictability of the things that INSO may influence, but what about INSO itself? Well, we can look at the Niño 3.4, the predictability of the Niño 3.4 region in CSM1. This is showing you the forecast scale change between the period 1951 to 1980 minus 1921 to 1950. And it's showing you the scale as a function of initialization month and lead time, where the dots are showing a significant shift in the distribution, basically. And we can play the same game, not just for the earlier periods, but we can work our way consecutively throughout the historical record to see if this change is monotonic or if there's some interesting shifts in predictability as a function of time. And what you can see is in CSM1, you get this nice monotonic increase in forecast skill from the early part of the record to the late part of the record, basically in all seasons, and again, in the later part of the record. So what about the other models, right? I started this talk by showing that all these other models are doing different things with respect to their future INSO variability changes. And it turns out that if you look at the forecast skill in these other models, you get very different answers. So this is the forecast scale of the Niño 3.4 region for the other 4 models, CSM2, GFDL SPEAR, GFDL ESM2M, and MPI. But I want to make the argument here that although the models give you different results for the future, I think they're all doing something internally consistent within their own modeling framework. And just to convince you of that, here are their different Niño 3.4 standard deviation changes for the wintertime once again. And you can see that the change in skill is going lockstep with the change in INSO variance. So if you look at something like CSM2, you can see there's an increase in variance and then a decrease in variance, which corresponds to an increase in skill to the mid-21st century, and then a decrease in skill. If we jump down to GFDL ESM2M, you can see that there's very little change in Niño 3.4 variance, and then a sharp decrease in variance, which corresponds to a minimal change in skill, and then a sharp decrease in skill. And things like MPI, where there's basically no change in forecast or in variability, there's very little change in skill. So even though the models give very different answers in the future, they all seem to be doing something internally consistent. So this is just for INSO itself, but then we can quantify this relationship on broader scales for global forecast skill. And we can do that by looking at this scatter plot, which is showing you global average forecast skill for SST in the wintertime versus the Niño 3.4 standard deviation in wintertime for each of the models. So every model is a different shape or a different marker type, and the color of the marker is telling you what the values of these two things are at different time steps or different 30-year windows going from the beginning of the record to the end. So darker colors are the beginning of the record and yellows are the end of the record. And this is specifically for skill at 6-month lead, but let's just focus on CSM1, which is the circles, and you can see that as time marches forward, Niño 3.4 standard deviation increases, and you get a corresponding increase in global SST skill. Something more fun might be like CSM2, which has an increase in variance and then a mid-century decrease in variance that's, again, corresponding to a global decrease and increase in skill, or the way around, global increase and then decrease in skill. And ESM2M, again, is doing this sharp decrease in skill after about 2020. And this is true not just at 6-month lead, but 18 months, 12 months, and 24 months as well. You get very similar relationships. So the mantra I'm going with here is that forecast skill goes as INSO goes. We may not know what INSO is doing in the future, but skill is going to follow, at least based on these model estimations. So with that, I'll summarize. INSO and its teleconnections are projected to change in the future, even if the nature of those changes are uncertain. Perfect model analog forecasts drawn from large ensembles suggest that seasonal climate predictability will also change in the future, but the sign and intensity of forecast skill changes are related to the sign and intensity of INSO variability changes. So forecast skill goes as INSO goes. So thank you. I'm happy to take any questions.
Thanks. Do we have any questions?
Yes, please.
So you started by saying that all the models are reasonable, but then they get very different answers. So if we think that these different answers in the future are forced response, I mean, they have different forced response. So how can they be both, all reasonable and have different forced response in the future?
Yeah, so when I say they're reasonable, I just mean that they look like observations as far as their spatial pattern and their overall variability and where they have peak power in their power spectrum. They have different biases with like westward extension, but they're just because they have different future projections or radiative responses doesn't necessarily mean that their internal characteristics aren't generally consistent with observations.
But it still means that the processes that are acting to give you this forced response, if you interpret the 21st century projections as a forced response, which is an open question, they have to differ, right? Otherwise, they will give the same answer. So,
yeah,
like if you take instead of doing the analogs as you did it, if you do some sort of sibling experiment, so you take the analog from one model to predict the other.
Yeah, you could do that for sure to see what's common across all of them.
And can you tell us what you would get from that?
I haven't done it, so I can't tell you what I would get. But
from I guess from what we showed at the end, it's probably easy to say that this is not going to work, right?
Yeah, I mean all the models.
If you take CSM1 to predict CSM2 or vice versa.
Yeah, I would imagine that there's not much common between the two.
Okay.
Sure. Yeah, I'm not entirely understanding your point, but maybe we can talk about it later. But yeah, go ahead.
Yeah, there's one in the chat. So from Jakob Schloer, great talk, Dylan. Why do you think the standard deviation of Nino 3.4 is correlated with the forecast skill? Is that necessarily the case?
So yeah, I think that the idea here is that as INSO becomes, let's say INSO were to increase in the future, it becomes a bigger hammer in the climate system. So as it becomes a bigger hammer in the climate system, it increases our signal to noise ratio in a forecast sense, and we're able to forecast something better. We're working on ways to quantify that signal to noise ratio to get a better sense for what that looks like as a function of time and space.
Oh, you're doing that, Alan?
Sure.
Yeah, good talk, Dylan. I'm just curious if you're able to quantify, how good an analog set you have as a function of time. I mean, could it be that you've got a less kind of well-matched set of analogs in present day versus in the future, you've kind of got a better kind of initialized ensemble? I mean, do you quantify that or look at that at all?
Yeah, so you can kind of get a sense for that by looking at the changes in the 0-month lead forecast scale, which there were differences. That sort of suggests that in the future, your analogs are better matches in the future. Another way to do that is by looking at, so we chose analogs based on global RMSE, and we could look at global RMSE of your analog fit as a function of time. And that's something that I'm actively calculating right now. Unfortunately, I can't do this in an hour on my computer. It takes a couple days at a time. It's just a lot of data to push through. But yeah, great suggestions. Thanks, y'all. Appreciate it.
Thanks a lot. So we'll move on to our next talk. This is a virtual talk by Jakob Schloer on using machine learning to characterize ENSO nonlinearities. So we can see your slides. It looks good. Oh,
We can't, he's muted.
we can't hear you though. Are you muted? Didn't look like he was muted because the things.
I don't think I'm muted. Do you hear me now?
Yeah, it was our problem. It's good now.
Okay. Cool. Okay, so yeah, thanks for the introduction. I'm glad I can present here. Sorry I cannot be there in person. I caught a cold and I hope I'll make it for the talk without coughing too much. I'm talking today about characterizing nonlinearities in the CESM2 ENSO dynamics using machine learning techniques. And this is a project I'm working on with Antonietta and Matt at NOAA currently. And I'm visiting NOAA for half a year because I'm actually a PhD student at the University of Tübingen. I'm advisor at Vidarta. And I brought here like a teaser where it's like this is forecast skill improvement due to nonlinearities at a 12-month forecast I'm seeing in the sea surface temperature anomalies. but you will see later how I get to this plots. Okay, so ENSO forecasts are generally done by dynamical or statistical models. And one model which is around for long already is like linear inverse models, which was introduced almost 30 years ago by Penman and Matrosova, and has since then been improved and developed. So limb skill is now comparable to the NMME forecast. More recently, neural networks have kind of entered the stage into subseasonal to seasonal forecasts and also ENSO forecasts. Just to point out here, the study made by Hamed al, where they used convolutional neural networks to forecast the NINO 3.4 for 24 months. So kind of naturally already arises the question if we cannot combine this model, like the longer, well-established model and neural networks. And can we improve forecasts with this? And can we not just forecast NINO 3.4, but also maybe like whole fields, because of we are interested maybe also in ENSO diversity and their impacts. I'm not the first one doing this. There's a study by Rodriguez et al. In 2021 already, but we do things differently there and improve upon their results, I think. Okay, so why would we do this? What's the reasoning behind? And that's, I think, we can take the perspective of seeing ENSO dynamics from a stochastic differential equation perspective, where we have the changes of our state vector being described by a deterministic part and a stochastic forcing of it. They both here generally could be nonlinear. And in the ENSO, the deterministic part would be the slow varying ocean dynamics, which would be stochastically forced by the atmosphere, like the higher frequency atmosphere. In linear inverse models, the deterministic part is basically assumed to be linear in dynamics, just described by this linear operating acting on the state. And the stochastic forcing is just assumed to be Gaussian white noise, so not state dependent and not nonlinear. And so if we have a forecast with a limb, we would have this data here, this time series, and 0 would be our initial state. We can do a forecast, let's say 24 months ahead, like here shown as, for instance, the blue curve. And this will be the first part of our model. So we can do a bit like we can be more general by saying the deterministic part does not necessarily only have to be linear, but it can also have a nonlinear part here. And this, we try to now model this nonlinear part using a neural network. And so here again in this figure, let's say this would be our blue, which is again our limb forecast, of the black the data, and we try to find some nonlinear part to it. But what is important here, we still have a stochastic, we still assume a Gaussian white noise stochastic forcing. And how do we do this? We use what is called a long short-term memory network, which is a recurrent neural network. And the advantage is here that the LSTM can aggregate information over time. So it has this kind of so different timescales can be captured in internal variables by so we kind of get like a memory in the network and over time. And this is able, therefore, to capture nonlinear and non-Markovian dynamics. And this will be our second part here of our model. So looking at this all together, we would have our initial conditions where we use the linear inverse model to do predictions. And then this are inputs to our LSTM, our neural network, which learns the residuals of this, so the nonlinear part, the R hat here is the nonlinear part. And we train this by using a mean square error loss on the data and the limb forecast plus the residuals. We can do a bit better here by improving here, or looking at including cyclostationarity, so the seasonality into this model. And we could do this at two places. We can use the cyclostationary limb, which was introduced by Shin in 2021. And we can also incorporate cyclostationarity in the LSTM by conditioning on the season. And therefore, we use here a feature-wise linear modulation. If you want to know more about this, talk to me maybe later. Okay, so the data we're using here is the CESM2 pre-industrial control end, where we use monthly sea surface temperatures and sea surface height in the tropical Pacific. Here on the right, I just show you of the El Nino and La Nina composites and sea surface temperature, normalized sea surface height. And so this gives us 1,200 years of data, which is great because, I mean, you know that machine learning techniques tend to be quite data hungry. And we split this into training and test data. One important thing is here we do the forecast in the principal component space. So because the linear inverse model requires computing of the covariance matrix in an inverse, so we have to do dimensionality reduction. And in everything we see in the following, it will be 20 principal components of sea surface temperature anomalies and 10 principal components of sea surface height anomalies, when it's indicated. Sorry, I have models which are only on sea surface temperature anomalies and models which are on sea surface temperature anomalies and sea surface height. The evaluation we do in grid space, and we use the skill score for this. And this is basically 1 minus the root mean square error divided by the standard deviation. And the nice thing is about this that 0 is basically a climatological forecast. And to not only look at maps, we look at averages in skill over the NINO indices, where we have NINO 1.2 to NINO 4. It's a kind of known, but then we also introduce NINO 5, which is in the west of it. Okay, so let's come to some results. So I did like a slew of experiments. It's a bit overwhelming, the slide, but I'll walk you through this. So what we have here is basically the skill of the NINO 3.4 over the different lag times, and this is the skill score. And what we have here in black is the persistence, which is like escape this plot kind of fast after 6-7 months. And then we have just as a comparison, we have just the pure LSTM forecast, where we have this stationary and the cyclostationary. We have the limbs, the linear inverse models, stationary and cyclostationary, and then we have all the different kind of combinations of limb plus LSTM. And so if we look at the pure LSTM forecast, this formed basically the lower boundary here of the skill curves we have here. Because one reason for this is that we think that learning the whole dynamics really just purely from a neural network, it's much harder than analytic procedurals. We think this might increase with more data, but we have to check this. Then we have the linear inverse models, which already do better. We have here in light blue the stationary linear inverse models, and including seasonality, here the purple and dark blue, already do have a higher skill, whereas adding sea surface height anomalies also increases the skill. And then we have here the best models, which are the combinations of the cyclostationary limb and the LSTM here, for instance, in red, the best one. And so now we can kind of, because we have all these different models, we can compare them and see what is the role of nonlinearities in the skill. And so here for instance, here it's a bit of also an overwhelming slide. We have different skills or skill scores, or actually differences in skill score of the cyclostationary limb plus the LSTM minus the cyclostationary limb, meaning we see what is the improvement due to the LSTM. We have here this from 1 to 24 months for different verification months. And we definitely see here that after 9 months, we get an improvement in skill here. And let's have a look at a bit closer. In one of the plots, here we see, for instance, for a 12-month lag time, the skill improvement for July. We clearly see that the nonlinearities seem to improve the skill in the Western and Central Pacific here. So we can also look at this with the different NINO indices here from east to west, where we see a clear increase in skill due to nonlinearities between 9 to 18 months in the Western Pacific. And this improvement forecast is initialized in July and December. And because we did all these experiments, I don't show this now, but we can compare basically the different skills and see that this is not due to the seasonal cycle, the linear, and we also kind of see that this improvement is not due to the ocean memory, what I kind of include when I use the sea surface height anomalies. So the question is, what could that be? And now we kind of think that this is due to El Nino and La Nina asymmetry in forecast skill. So here again, the same plot as before in the upper row. And then if we only look at the skill of El Niños, we don't see this pattern in the Western Pacific here. But what we see is that when we look at La Niñas, that we pick up a similar improvement in skill for La Niñas, as we see in the overall improvement. So one of our hypotheses that at least partially the nonlinearities can be explained, the improvement due to nonlinearities can be explained by ENSO asymmetry, meaning that La Niñas are better forecast. We can do a better forecast for La Niñas than for El Niños, which goes very along with also what Nathan already showed before. Yeah, so to conclude, we have, with limited amount of data, S2S prediction is hard for pure neural network methods. So that's why it makes sense to look at residuals. Nonlinearities and non-Markovianities seems to improve predictions for bigger than 9 months. And the predictable nonlinearities are likely due to El Niño-La Niña asymmetries. And as an outlook, we like to disentangle the nonlinearities more with using idealized experiments. And we like to apply this to observational data using transfer learning. And with this, I'd like to thank you for your attention, and Antonietta, Matt, and Vedanta for their advisories and good feedback and everything. And I'm happy to answer questions via mail or in the chat or now.
Thanks. Are there any questions online or in the room? Laurent?
Was there any sensitivity to the number of PCs or EOF you're retaining? So isn't there a risk to sample noise because you retain a lot of PCs and EOFs?
So yeah, we check for this. So we look at, so there's like, we did kind of an ablation study where we varied the number of principal components for both sea surface temperature anomalies and sea surface height, and looked at whether the results changes. And then there's kind of like a threshold where you say you don't gain any more by using more principal components, because you make also the problem harder in terms of you have more degrees of freedom, but you capture enough of the autocorrelation. Does this answer your questions? I'm not 100% sure.
Yeah, we're just trying to see whether there's a more physically based criterion to select the number of EOFs, or whether you have thought of using rotating EOFs, for example, because we know that, I mean, you're retaining 20 EOFs, so I don't know how much variance for they explain in the end. So just, I was just wondering if there was a risk that you're just sampling noise, basically, so which is not very useful if you are thinking of neural network approach. So
I'm like, even if there would be noise for the neural network, if you regularize it good enough and train it well, that you get like the minimum in the validation set, because we do validate our model against like a data which hasn't been seen for training, right? So it should not pick up necessarily the noise then.
We have one more question in the room. I guess in the meantime, if you could stop sharing your screen, then we can get the next speaker up. Nicola?
Yeah, for what it's worth.
Let's talk, Jacob. Do you think you'd gain significant value by adding other variables like heat content or wind stress, or it would just be kind of a minimal increase in skill?
It could degrade it. But.
So yeah, so what we definitely see is that there is a huge improvement, like at least for in the linear case, we definitely see an improvement in skill adding ocean heat content or other variables which capture kind of the deeper ocean. So for instance, here we use sea surface height, and we clearly see an improvement between 3 to 9 months in this initialized in the spring. So basically what we see is that adding sea surface height basically overcomes the spring predictability minimum. Basically, there's a minimum in predictability in the spring usually before, and so adding this ocean variables improves among this. But what we actually see is that the nonlinearities the neural network does not pick up the signal. If you only look at sea surface temperature anomalies, it improves the forecast skill at later lead times than including this ocean variable. So there is an improvement with the ocean variable, but that's not what we see with a neural network. It's just a different effect.
Okay, thank you very much. We'll move on to the next speaker, Jiali Liu. We're hearing more about ENSO forecast skill in a changing climate.
Hi, everyone. I assume you can hear me well and see my screen. Today, I'm going to talk about ENSO forecast skill in a changing climate using the modern analog technique. As Nathan's and Dylan's talk have shown, modern analog is such a simple but powerful tool that not only provides a forecast skill that is comparable to that generated by numerical models, but also provides a very straightforward tool to evaluate the performances of the state-of-the-art models, for example, CMIP class models. Without further ado, I'd like to start with the motivation of this work. The screenshot here was taken from PSL seasonal forecast web page. Basically, it shows the real-time ENSO predictions using a couple of empirical dynamic models, for example, linear inverse model and model analog technique. The ENSO prediction was taken from last month in January, and we can see we're currently in La Nina condition, followed by an El Nino condition in the upcoming winter in 2023-24. In order to evaluate how the accuracy and skillfulness of the real-time ENSO predictions, we utilize the model analog technique and make 20th century ENSO hindcast to evaluate the ENSO predictions and predictability. Previous studies, for example, Ding et al. 2018 shows that model analog is actually comparable to the skill generated by numeric models, for example, NMME showing the bottom layer. However, this previous work only goes back to 1982, which might not be sufficient to diagnose and understand the long-term variation of the ENSO forecast scale. Therefore, one of the motivations of this work is to extend the previous ENSO hindcast to see how the ENSO forecast scale might evolve over time. Here, this plot shows the anomaly correlation of Nino 3.4 at 3 different time leads, 6, 12, and 18 months leads. Basically, I divided the entire period into 30-year moving window and computed anomaly correlation scale at each chunk of period for 7 different SST verifications. The gray shading here indicates a cross verification, which means we use one of the SST datasets to select for model analogs, but verified against the other 6 SST datasets, which sort of gives us an estimate of how much the ENSO forecast scale is due to the uncertainties arising from the observations. So we can see the ENSO forecast scale here is quite robust across different verifications. And another point here is that ENSO forecast scale underwent multi-decadal variation with a minimum in the middle of 20th century. Besides the deterministic scale metric I showed in the previous slide, we also explored some probabilistic scale metric for the categorical La Nina and El Nino conditions. Here I showed the ROC score, which basically measures a hit rate versus a false alarm rate. For a perfect system, the ROC score is equal to 1, which means there is no false alarms. If the ROC score is less than 0.5, it means our predictions are no better than random guesses. Then we can see our predictions for La Nina and El Nino conditions are generally skillful, as most of the values are greater than 0.5. And then if we have a look at the long-term variation of the ENSO forecast scale, we can see, similar as I showed in the previous slide, probabilistic scale metric also underwent multi-decadal variations with a minimum scale in the middle of 20th century. Another point I want to make here is that if we have a look at the hatching area over here, it indicates the differences between predicting El Nino condition and La Nina condition are significantly different. So as indicated in the green circle over here, we can see in recent periods, La Nina has been more predictable than El Nino. However, if we go back to a century ago, there was a pronounced period where the El Nino is actually more predictable than La Nina. So we tend to argue that the recent period where La Nina is more predictable than El Nino might be just temporary. The question now is that what might be causing the ENSO forecast scale changes during the historical period? So on the right-hand side here, I show the 30-year moving variance on Nino 3.4 index based on seven different SST observations. And we can see the ENSO forecast scale on the left-hand side corresponds well with the variance change. That is, the greater the variance, the more skillful the ENSO forecasts are. However, question still remains. Now we try to figure out how much we can attribute the past multi-decadal variation of ENSO forecast scale to climate change versus internal variability. To address this question, we defined 3 experiments in our work. The first experiment uses pre-industrial control simulation to select for the model analogs. And the second, it's worth noting that the results shown in the previous slides are all based on pre-industrial control simulations. The second experiment uses the large results by comparing the pre-industrial control simulation showing the blue curve with a large ensemble simulation showing the red curve. We can see ENSO focus scale increases, especially at longer leads under a changing climate scenario, which sort of suggests that climate change might have a positive impact over the ENSO focus scale. Then we have a look at seasonality of Mini 3.4 focus scale for different experiments. And we can see in the for the recent period, the second year ENSO scale becomes more predictable under a changing climate scenario, which again suggests that ENSO focus scale might be increasing in climate change. To eliminate the uncertainties from the observations and to separate the internal variability and the external forcing, here we also considered a perfect model experiment. So on the left-hand side, I show the 30-year moving standard deviation of Mini 3.4 in CESM2 large ensemble, where the red curve represents the ensemble mean. We can see that most of the ENSO variability has been smoothed out, leaving only a monotonically increasing ENSO trend that reflects the externally forced ENSO response during historical period in CESM2 large ensemble. If we compare these various change with the observed various change, we would see that we tend to conclude that the ENSO variability is mostly internal generated, as the ensemble mean fails to reproduce the minimum variance in the middle of 20th century. Then, if we compare the standard deviation with the corresponding focus scale of the in the perfect model experiment, we can see there is an evident relationship between the standard deviation of Mini 3.4 and the focus scale. To illustrate this relationship a bit more, here I show the scatter plot by presenting a numeric relation scale on the y-axis and the standard deviation on the x-axis for 3 different time leads. We can see as we increase the time leads, the ENSO focus scale becomes more correlated with the corresponding variance. For example, in this case, if we increase the standard deviation of ENSO by 1 sigma, the corresponding ENSO focus scale might be increasing by 0.36 at 18 months lead in this case. Finally, since each ensemble member simulates ENSO trajectories quite differently, we carefully selected a few that could correctly reproduce the minimum variance observed in the middle of 20th century, as indicated in the colored curves here. And then we also checked the corresponding focus scale for those ensemble members. And then we saw that the ENSO focus scale decreases due to the reduction of variance in the middle of 20th century, which is quite similar as Dylan concluded in his work. Sorry. To sum up, we first showed that ENSO focus scale underwent multi-decadal variations in both the deterministic and probabilistic scale metrics with a minimum scale in the middle of 20th century. And then we separate the La Nina and El Nino conditions. We show that in the recent period, La Nina has been more predictable than El Nino. However, this difference in the recent period might be just transient. In the follow-up work, we try to address the question, how much can we attribute to the past multi-decadal variation of ENSO focus scale to climate change versus internal variability? Based on the current results, we found that ENSO variability is mainly internally generated. If external forced ENSO variance increases in changing climate, as indicated in the CESM2 large ensemble, we might expect that the focus scale of ENSO will increase correspondingly. With that, I'm going to stop here and take questions if there's any. Thanks.
you. Do you have any questions? Yep, Nathan?
Yeah, that was a great talk, thanks. I'm curious about this second conclusion, that you're saying that you had this period in like the early 20th century, right, where it looked like El Nino scale was larger than La Nina scale. Have you looked into why that might be the case? And secondly, have you seen this result in any of your other kind of more perfect model experiments, that El Nino scale is greater than La Nina?
Yeah, the conclusion is based on this. And first of all, I didn't conduct this for the perfect model experiment. And yeah, so yeah, that's all I can say. Yeah, I didn't do, I don't know how it looks like in the perfect model. But in this case, yeah, we do find El Nino is more predictable in the early 20th century.
I was wondering whether you've looked at, you picked out some members that looked like the observations in terms of the variations in skill. Have you tried to see whether there's anything else common to the observations there, like what's going on in the Atlantic or the PDO or something that might explain variation?
First of all, my model analog is selected based on like 30 south to 30 north. And my focus is like those variability in those regions. So right now, I'm not sure for PDO and Atlantic regions.
Okay, thanks.
Thank you.
All right, we'll move on to the last speaker of this session. That's in-person talk by Steve.
Audio good? All right. So I'm going to talk about some work that a group of us have been doing to address this question using CESM prediction systems. And these are preliminary results. I really want to emphasize preliminary because these experiments are only a couple weeks old now. And we're following a CLIVAR tropical basin interaction protocol doing Atlantic hindcast pacemaker experiments. So just some brief background. This is not comprehensive by any means, but I wanted to give you a flavor of sort of where this question is coming from. So in 2007, Kienle-Seid and Latif showed, based on observational analysis, that the tropical Atlantic is correlated with ENSO, with the former leading the latter by about 6 months. And then later, they did some pacemaker seasonal prediction experiments with and without restoring in the tropical Atlantic. The standard experiment here is contrasted with the experiment where they do pacemaking in the tropical Atlantic, and they highlight this improvement in skill for these large ENSO events compared to the control, suggesting that the Atlantic is adding some information for these large positive El Nino events. And then in 2012, Ding et al. Did an Atlantic pacemaker experiment using the MPI model, full SST restoring in the tropical Atlantic, and they were able to recover this anti-correlation between the tropical Atlantic and the Pacific. Now the lag has switched, so now this is Atlantic leading the Pacific by about 6 months. So some evidence that this is evident in coupled model simulations. In 2021, here's a paper that did an analysis of available seasonal prediction systems, including some that were nudging in the Atlantic. And they're highlighting this correlation between skill in summertime Atlantic 3, so Atlantic Nino in sort of year 1, and how that correlates with SON, Nino 3, DJF, NDJ, Nino 3. So there's some evidence that models that do a better job of predicting the tropical Atlantic also do a better job with ENSO prediction. Another paper came out in 2019. This was an analysis of observations and CMIP5 historical and projection runs. This top plot here shows the running correlation of Atlantic 3 with Nino 3. From observations, you see that this negative correlation really kicks in after 1980. And many CMIP models are able to simulate this connection. CESM1 is in here somewhere. So, and the OBS is in black here. So this is sort of a teleconnection that models are somewhat able to represent. And so there's hints that, ENSO predictability could benefit from increased skill in the tropical Atlantic. But then Ingo Richter came out in 2022 with a paper, and I don't have a plot, but this quote is from that paper saying that the results indicate that in this particular GCM, the tropical Atlantic mostly acts as a negative feedback to ENSO by accelerating the decay of events. It has little impact on the development of ENSO events. So there's some uncertainty in the literature regarding what role the tropical Atlantic plays in ENSO seasonal prediction. And so that's the background for coordinated pacemaker experiments organized by the Clivar Tropical Basin Interaction Research Focus Panel. We're calling this TBI COEX. Co-chairs of the panel are Ingo Richter and Yuko Okamura. And we got entrained in this effort starting, I think, in 2021 when discussions started about what would a coordinated protocol look like. And these discussions have revolved around both uninitialized, so standard, and initialized or hindcast pacemaker simulations with SST restoring in each of the tropical Atlantic, Pacific, and Indian basins. And so over the course of the past year, we've kind of decided on a common protocol, common time period for running experiments, common SST restoring target, SST restoring region, primarily in the deep tropics with linear tapering out to the subtropics. We want at least 10-member ensembles. We'll use CMIP6 forcing. And for the initialized hindcast pacemakers, we really want to emphasize this February 1st initialization and do other ones if possible. But there's still several undecided elements to this protocol. So what's the method for generating a hindcast control, whether to use full field or anomaly restoring, and what the restoring strength should be. So we've kind of been the guinea pigs and have pushed forward and are testing this protocol, and maybe it will become finalized. So what we're doing is using the CESM2 SMILE as the hindcast control. I'm not going to introduce this. Many in both working groups are familiar with this. It's our seasonal to multi-year prediction system initialized quarterly using the CESM2 model. But I do want to point out that CESM2 SMILE has good, and I would say competitive, ENSO prediction skill. So this is showing the skill for DJF Nino 3.4 as a function of lead time from different initialization months. And I really want to highlight the February initialization down here. This is a 10-month lead prediction of DJF Nino 3.4. We get correlation scores above 0.6. You can see the time series here. Quite small ensemble spread and good prediction for these large ENSO and La Nina events at this lead time. So this is our control. And then just to further highlight the skill here, our February initialization, which is the blue line here, outperforms all of the models that contributed to NMME, which is the red shading here. So in particular for this initialization, we think we've got a skillful system. All right, so here's the hindcast pacemaker experiment that I'll be showing results from. It's the equivalent setup to CESM2 SMILE, except SST anomalies are restored to observed anomalies in the tropical Atlantic. So the target SST is CMIP6 AMIP SST. We're doing anomaly restoring, so that means we're restoring to the SMILE lead-dependent climatology plus the observed monthly SST anomalies. And so what that means is that this experiment has the same lead-dependent climatology as SMILE. So we haven't changed the climatology of the prediction system. We've just added the observed anomalies in the tropical Atlantic. Again, this region, 10 south to 10 north with linear tapering, pretty strong restoring, 10 days over 50 meters, if that means anything to you. And so this experiment is a small ensemble, 5 members, initialized each February 1st from 1980 to 2018 and integrated out 23 months. And just to show you that the experiment is working, here I'm showing forecast month 5. So this is June. Monthly anomalies. This is Atlantic Nino, black is observations. Blue is the SMILE control. So we've got no skill at predicting Atlantic Nino at forecast month 5. And here's TBI Atlantic, so closely matching the observed anomalies. And both systems have pretty good skill at predicting Nino 3-4 at 5-month lead. So here's the result. Here's the main slide. This is showing skill as a function of lead time on the top for Atlantic Nino and bottom Nino 3-4. What you see is in SMILE, the Atlantic Nino skill starts off modest, a little bit over 0.4, and drops pretty rapidly. The summer skill, which is kind of what we think of as the primary influencer on subsequent winter ENSO development, is pretty low. When we do TBI Atlantic, of course, by design, we've got very high skill and in Atlantic Nino region. But we're comparing here a 5-member ensemble to a 20-member ensemble. So the gray curve here shows SMILE resampled. So this is the mean 5-member skill from SMILE and the uncertainty in gray shading. And below, we see Nino 3-4 skill. So this was the shocking, surprising result to me. Almost no improvement in Nino 3-4 skill in DJF of year 1. So the much improved representation of tropical Atlantic variability in TBI Atlantic not having an impact on winter ENSO. What it does have an impact on is the subsequent decay of ENSO skill in the spring. So you can see a clear deviation from the SMILE 5-member ensemble in blue here in March, April, May, June, July, August. So just showing you the time series just to hammer that point home. Here we're looking at DJF Nino 3-4. Here's the SMILE 5-member ensemble. Here's TBI Atlantic 5-member. It's hard to see any difference here. SMILE 5-member is very skillful at getting these large events, and TBI Atlantic not showing major improvement there. No obvious improvement to my eye. However, in spring, you do see some improvement, right? So the correlation score is higher, and in particular, you see a better prediction of the in the 1980s and 90s compared to SMILE control. So we can look then at the kind of broader skill here. These are maps of correlation skill for surface air temperature. On the left is SMILE, and on the right is the TBI Atlantic experiment. Of course, by design, we've got high skill in the tropical Atlantic, and this is as a function of lead going down. But we don't want to compare to 20-member SMILE. We want to compare to 5-member SMILE. So when I switch back and forth, you can see how the skill drops drastically when you only have 5 members. Now you can see that TBI Atlantic is outperforming a 5-member SMILE, but how much of this performance gain is coming through sort of interesting dynamics as opposed to the imposed tropical Atlantic forcing? That's the question. So here, just to show you the skill differences, this is the ACC skill difference, TBI Atlantic 5 minus SMILE 5 for surface air temperature, precipitation, sea level pressure. In the interest of time, I'm just going to focus on winter, lead month 10. So you can see some, skill improvement in regions of interest like Western Canada, and we also see skill improvement in precipitation. But as I pointed out, there's no real improvement in ENSO skill. So where is this skill improvement coming from? If it's not coming from ENSO, maybe we don't care about it if it's just coming from the restored SST here. So to try to get at that question, I looked at the ENSO teleconnections. These are all regressions of DGF fields on DGF Nino 3-4. This is at lead month 10 for the prediction systems. And the left column here shows the observed teleconnections for SST, surface air temperature, sea level pressure, and precipitation. And there's a lot of information here, but the main takeaway is that these two prediction systems are much more similar to each other than they are to OBS. So all of the teleconnection biases that are in SMILE, like this excessive cooling over much of continental US, are also present in TBI Atlantic. So it doesn't appear that the Atlantic restoring is either improving ENSO or really improving the ENSO teleconnections in wintertime. All right, to summarize, we've done a successful test of this hindcast pacemaker protocol with CESM2. The evidence for improved ENSO skill appears to be weak in this system. There's less skill reduction in spring of forecast year 2, and that's consistent with Ingo Richter's recent work. Maybe there's minor improvements in ENSO teleconnections in forecast year 2, but I'm grasping at straws to find them. The strong Atlantic influence on DJF1 may be limited to specific events, so maybe we need to sort of focus in on case studies with a larger ensemble. And it could be that the high skill in the SMILE control might explain some of the discrepancy with earlier studies that have shown a significant impact of the tropical Atlantic. I think it's questionable whether these forecast year 2 improvements are realizable because it's probably beyond the tropical Atlantic predictability limit anyways, so should we care? And also another comment on the experimental design, it's difficult to disentangle these regional skill enhancements in surface climate. Are they the direct result of imposed SSTs, which is sort of a trivial result, or they come about through Atlantic modulation of ENSO and or ENSO teleconnections, which is a more interesting result? Hard to answer these questions. But I would say this preliminary analysis suggests that this experimental design is sound and that a multi-model application could be useful. Thanks.
Thanks. Any questions for Steve? Yep.
I might have just missed this, but were you checking against the perfect model or against observations to evaluate skill?
This is an initialized prediction, so we're evaluating against observations. Yep.
There's a question in the chat from Sanji. Great experiment and talk. Forecast climatology is a function of initialization month and lead time. You talked about lead time dependency. How about the initialization month dependency?
Yeah, that's kind of future work, right? So we've done February initialization. I think we'd like to try to expand this to May and August. And I think it would be actually more interesting to do November and see if sort of ENSO decay into the spring in a lead time window that is potentially predictable in tropical Atlantic would give us skill improvement, but remains to be seen.
There's another question in the chat from Evan Meeker. There have also been studies that the North Pacific can be a precursor to ENSO events at similar timescales to the tropical Atlantic of the order of 6 months. Would it be worthwhile to run a Pacific pacemaker in this way, following the same line of reasoning?
It's an interesting idea. I have not heard that proposed, sort of an extratropical pacemaker. The TBI panels is clearly focused on tropical basin interaction, so we're planning to do tropical Atlantic, then tropical Pacific, and tropical Indian. But you know, we've kind of established the framework for performing these experiments. We've got the SMILE control. That's a great thing for a working group member to take up and explore.
Yeah, definitely. So there's one more in the chat from Antonietta. How large are the tropical Atlantic biases in SMILE?
Large, and you know, that was certainly a lot of my effort exploring this experiment was testing whether we should do full field restoring and try to eliminate the bias. That would certainly probably improve the teleconnections, but if you hammer down bias in one region, it pops up in another. It's a really problematic experiment to design. So in the end, I felt that anomaly restoring was the way to go, and just don't try to mess with the climatology.
Okay, that concludes this first session. So we have a break now, and we'll come back at 10:40. So thanks all the speakers for staying on time and for some great talks.
There's lots of places.
All right,
You were not-
we're live. We're gonna get going again,
I'm not one of them.
and we're transitioning into the Earth System Prediction Working Group. Part of the agenda. The next talk is by Danny Du.
Can everyone hear me clearly? Clearly?
Yes, we can.
Good. Hi everyone. I'm Danny, and I'm currently a fourth-year PhD student at University of Colorado Boulder. And today I will be presenting some results from our recent project on the potential increase in MJO predictability under global warming. And in the beginning, I would love to acknowledge the contribution from my advisors, Anish Subramanian and Wei Qing Han, as well as our two other collaborators on this work, Will Chapman and Jeff Weiss. The Madden-Julian oscillation is the eastward propagation signal of the large-scale circulation and deep convection in the tropics. And it's usually with a period of 30 to 90 days, and it's the leading source of predictability in the tropics at the time scale of subseasonal to seasonal. Usually, when we are monitoring the MJO activity, we use the real-time multivariate MJO index, the RMMI, and it's computed using the EOF analysis on the three combined fields of the zonal wind at 850 millibar, the zonal wind at 200 millibar, and the outgoing line radiation, which is a good proxy of the deep convection over the tropics. After doing the EOF analysis, we would be obtaining two leading EOF modes and their corresponding principal component time series, and there are RM1 and RM2 respectively. With RM1 and RM2, we will be able to determine the amplitude and the location of the MJO active convection. Here on the right, we show an MJO phase diagram with the RM1 being the x-axis and RM2 being the y-axis. So in this diagram, the farther away a point is from the origin, the greater the MJO amplitude is. Also, we can clearly see that the RM1 and RM2 are dividing the entire phase diagram into 8 phases, with each one representing some physical locations in the tropics. In this animation, we would have a more straightforward impression on how we can use RMM phases to characterize the location of MJO active convection. So here, the blue color denotes more rain. So it means the active MJO convection. And on the upper right, we can see at the RMM phases is changing. The MJO signal is propagating from the Indian Ocean to the maritime continent and then to the Western Pacific eastward. Under global warming, we know that the MJO behavior is changing. The previous studies have shown that the MJO duration over the Indian Ocean is decreasing under global warming, while the MJO duration over the Indo-Pacific maritime continent is increasing. And several other studies have also shown that the MJO amplitude is also changing under global warming, with larger amplitude MJO events occurring more often under a warming climate. So with the behavior changing in both the MJO propagation and the MJO amplitude, we ask this question: is there a systematic change in MJO predictability under global warming as well? To investigate this question, we would like to evaluate the MJO predictability over the past century. And currently, the most common practice in estimating MJO predictability is to use the ensemble forecast from numerical models. And the metric is to use the bivariate anomaly correlation coefficient, ACC. So usually when we want to assess the prediction scale of MJO, we would be comparing the RMM1 and RM2 from the model output with the observational RM1 and RM2. However, when we are evaluating the MJO predictability, we will be comparing one model ensemble with the rest ensemble mean, with the ensemble mean of the rest ensemble members. And using this ACC method and using a 30-year window, one initialization per year and 51 ensemble members, and from the ECMWF seasonal forecast, we will be able to have an MJO forecast predictability time series over the past century, as shown in this figure with the black line. And we can clearly see that the MJO predictability has gained a significant increase over the past century. And to assist this result, we also show the ACC time series at a forecast lead of 40 days. And we can see at a forecast lead of 40 days, the ACC time series is also increasing. And the two lines are telling us the same story, that the MJO predictability is increasing over the past century. However, this method would require the existence of this kind of forecast, a large ensemble size, and enough initializations. So with this method, though we can tell that there is an increasing MJO predictability over the past century, we cannot investigate whether or not this increasing trend is caused by global warming, because we are lacking a control group with only the pre-industry conditions. Therefore, we seek an alternative method to answer our question whether or not the increasing MJO predictability is caused by global warming. And this new method is the weighted permutation entropy. And the lower the weighted permutation entropy, the less random our time series is, and therefore the higher the predictability of our time series. And the mathematical details of how to compute the weighted permutation entropy has been recorded in a lot of existing references. Here, we'll just use a very simple example to illustrate how we can simply compute this WPE quantity. So with such a given simple time series, the first step would be choosing the time length and the time delay with xim tau. So m is the length of our delay vector, and the tau is the time delay we'll be using to pick elements from our original time series to reconstruct our delay vector. So here in this example, we'll use the time delay to be 1 and the time length to be 3. The step 2 would be to characterize the segments into each permutation by the order of each element in the segment. So the first segment from this time series would be 1, 2, 3, and we are using ordinal analysis. So the smallest element is the first one, the second smallest element is the second one, and the largest element is the third one. So it would correspond to an ordinal permutation 0, 1, 2, as shown here. And then the second delay vector in this time series would be 2, 3, 4. And because it's also a sequential increasing vector, we would also characterize it into the first permutation. The third segment from this time series would be 3, 4, 2. And here, this time, 2 is the smallest element, 3 is the second smallest element, and 4 is the largest. So the ordinal permutation of this element would be 1, 2, 0. Therefore, this segment will be characterized to the 1, 2, 0 permutation. And using the same technique, the same ordinal analysis, we would be able to characterize each time delay vector into their corresponding ordinal permutation. After doing this, we can weight the probability distribution function by the variance of each segment, and then obtain the weighted probability distribution of each permutation as shown here as PW pi. And then we can follow the formula to calculate the weighted permutation entropy. And it is just a varying version of the well-known Shannon entropy. And using the new method of weighted permutation entropy, we analyze the coupled error 20th century reanalysis with the time length 3, which would correspond to 6 permutations at most, and then use the coupled error reanalysis to 20th century project. We further use a 10-year running mean time window to compute the weighted permutation entropy. In this figure, we have three rows and 4 columns. So each column corresponds to one MGL related time series, the RM1 time series, the RM2 time series, the MGL amplitude, and the MGL propagation. And each row corresponds to the different time delay parameter we chose to compute the result. The first row corresponds to tau to be 2 days. The second row is tau equal to 3 days, and the last panel corresponds to a tau equal to 4 days. And for each subclass here, the y-axis is simply the weighted permutation entropy, and the x-axis is the year. So we can see during the past century, among all 4 MGL related time series and using different time delay parameters, we'll see that there is a consistent decreasing trend in the weighted permutation entropy. And recall that in the previous slides, we said that the lower the weighted permutation entropy, the higher the predictability. So such a decreasing trend in the weighted permutation entropy would be translated into a increasing trend in the MGL predictability, which is also consistent with the result we obtained from the model ensemble forecast method. And then we can further answer the following question: is the increasing MGL predictability caused by global warming, or it's just the centennial internal variability? And previously, because we don't have the ensemble forecast initialized from the pre-industry condition, we cannot answer this question. But now, since the weighted permutation entropy is more flexible and it can even be applied to the simulations from the CMIP6 models, we can easily answer this question by picking a good model that can simulate the MJO behavior. And here we choose the CESM2 model to test our assumption, because we know that CESM2 model has a good representation of the MJO structure and the MJO propagation. And we analyze the control run from CESM2, as well as the historical runs with 10 ensemble members from CESM2 and 3 ensemble members from CESM2 Wacom, and also the SSP 585 future projections with 3 ensemble members from CSM2 and 5 from CSM2 Wacom. By comparing the historical run with the control run, we will be able to see the fingerprint from the existing global warming. And by comparing the SSP 585 future projection with control run, we will be able to see under a more severe global warming how the MJO predictability will be changing. And the first step in doing such analysis would be to compute the weighted permutation entropy time series in each simulation and the future projection. And the second step would be to estimate the spread of the weighted permutation entropy slope from the control run, and it would tell us the range of the internal variability of how the MJO predictability can change. And recall that a negative weighted permutation entropy slope corresponds to the increasing MJO predictability, while a positive weighted permutation entropy slope corresponds to a decreasing MJO predictability. And the third step would be to compare the historical run or the SSP 585 future projection with the control run to see the influence of the external forcing away from the internal spread. Here in this figure, we show the historical run versus the control run. In the figure, the blue bars are just the weighted permutation entropy slope spread estimated from the control run, and the dots and triangles are the weighted permutation entropy slope fitted from each historical run ensemble members. And the vertical blue line here is the WPE slope mean estimated from the control run, while the vertical red line here is the mean weighted permutation entropy slope computed from the historical run ensemble members. And here we can see that the dots and the triangles, they're basically still within the spread of the blue bars, which means the influence of the external forcing here, in this case, the global warming, has not yet emerged from the internal variability of the MJO predictability change. And especially for arm1, arm2, and amplitude, though the dots and triangles are still within the internal spread, they are biased to the negative, and the mean of the historical runs are significantly more negative than the mean of the control run. However, for the MJO propagation, the dots and triangles, they're not only within the spread, and they're also not significantly biased. With this figure, our conclusion would be that the increasing MJO predictability during the past century might be a result of both the internal variability and the global warming forcing. And to further split the impact from the internal variability and the global warming, we compare the control run with the SSP 585 future projection with more severe global warming. And similar to the previous slides, the dots and triangles are the WPE slope fitted from the SSP 585 ensemble members, while the blue bars represent the internal variability estimated from the control run. And now in this case, we can see the dots and triangles are well separated from the internal variability, which means that global warming indeed can lead to increasing MJO predictability. To explain why under global warming the MJO predictability is increasing, the physical mechanism behind this question can be very complicated. However, here we'd like to give a simple answer from a mathematical perspective, because in the weighted permutation entropy computation formula, it's basically just to extract the information from the weighted occurrence frequency of each permutation in the ordinal analysis in the time series. Therefore, here in this figure, the x-axis are the time, while the y-axis are the weighted permutation entropy the weighted occurrence frequency of different permutation entropy. And here we can see the occurrence frequency of the dominant patterns of the dominant permutations are becoming increasingly dominant. For arm 1, arm 2, and the MGL amplitude, it's the increasing and decreasing pattern becoming more and more dominant. And for the MGL propagation, it's the eastward propagation pattern becoming more and more dominant. And intuitively, if some dominant patterns are becoming more dominant, then it means the MGL behavior is becoming more and more regular and therefore more predictable. And we also show a mathematical proof here by just doing the time derivative of the WPE and attribute the contribution to different permutations. And by doing this kind of analysis, we can conclude that the increasing MGL predictability is indeed contributed by the increasingly dominant patterns in the MGL behavior itself. So in summary, during the past century, both the ensemble subseasonal forecast and the reanalysis data indicate an increase in MGL predictability. And when examining with the CESM2 model ensemble, we find such an increase in MGL predictability is caused by internal variability and the external forcing, global warming. And under more severe global warming, the MGL tends to be more predictable. And the MGL gains more predictability through showing more organized patterns. And with a range of 10 days, the oscillation patterns and the eastward propagation patterns are occurring more and more frequently, therefore making the MGL more and more predictable. Thank you, and please feel free to ask questions.
Okay. In the interest of time, I think we have to move on to the next speaker. If you have questions for Danny, you can ask them in the chat.
How do we do that?
Jago Richter will be the next speaker, and hopefully we can get Eniola his technical issues worked out to follow you.
Good morning, everybody. Can you hear me okay?
Yes.
Great. All right, so today I'm going to report on a study that we started quite a while ago on subseasonal predictability from atmospheric land and ocean initial states. And I'd like to acknowledge all the people that contributed to this work, including Sasha, Tegan, Steve, Sanjeev, Nick, Paul Diermeyer, and Gokhan. So we set off on this study a while ago with the basic question or the basic goal to quantify how much subseasonal predictability comes from the initial state of the atmosphere, land, and ocean and sea ice. So basically to verify this diagram on the right that Paul Diermeyer made quite a while ago, which is supposed to be representative of predictability of mid-latitude surface temperature over land. And we're going to focus on the subseasonal window, which is right in here, so weeks 3-4 and weeks 5-6. And we expect the atmosphere to be a huge contributor in the early days, but in a subseasonal window, we expect contributions from the land, ocean, and the atmosphere. So we ran a series of experimental reforecast suites to test exactly how much predictability comes from these. And we started just with a couple, and now we've completed the set because we just weren't seeing things that were unexpected. So in addition to the standard reforecast set that's from 1999 to 2020 with weekly initializations, basically following the sub-X protocol, we reran the suite 6 more times. And in each suite, we changed out either 1 or 2 initial conditions from one or two monocomponents to climatology. So for example, the CLIMO ATM suite will have climatological atmospheric initialization at the beginning of the forecast, and the ocean and the land model components are initialized as normal. And similarly, for example, the CLIMO land and CLIMO ocean suite will only have realistic atmospheric initial conditions, and land and ocean are set to climatology. So running all of these combinations, and then finally we ran a suite in which we had climatological initial conditions for all the model components because we really needed that to quantify these contributions. All right, so what I'm showing here is the anomaly correlation coefficient for the first set of the forecasts. So on the left, we have the standard forecast, and these top channels go from weeks 1-2 to weeks 3-4 down to weeks 5-6. And we see that the scale for 2-meter temperature really drops off from weeks 1-2 to weeks 5-6. And this is very similar to what all the other subseasonal models are doing. And you see the drop is mostly over land. There is a lot more scale over in the oceans on these time scales. Okay, so what happens when we take out their realistic atmospheric initial conditions? Well, firstly, we see in the weeks 1-2, there is a very large drop in ACC over the land areas and not so much over the ocean. And then similarly over weeks 3-4, but by the time we get to weeks 5-6, all the areas that are stippled, they're not significantly different for the standard forecast. So what this is showing us is that the atmosphere has really strong impact, not only in the weeks 1-2, but also in weeks 3-4. When we go to the Clima land suite, this is where we started seeing our first surprise. So when we replace the realistic land initial conditions with climatology, we do not lose any skill in the first 2 weeks. And as a matter of fact, we really don't lose much skill in weeks 3-4. So over selected regions, over South America and parts of Africa, as a matter of fact, we gain skill from changing from realistic initial conditions to climatology. And similarly in weeks 5-6. So there's something in our model that is not working the same way as we expected. And we've had lots of conversations about this with Sanjeev, Paul Dermeyer, and even the land group. And what we think it's coming down to is that the coupling in CSM2 may be a little too weak, although we're still investigating that theory, but we're definitely not seeing what we expected to see, this strong coupling between the land and the atmospheric initial conditions, because we're not getting any gain of skill from realistic land initialization. All right, and when we move on to the ocean, we also were a little surprised by what we saw, but not as much as with the land. So in the first 2 weeks, we don't expect the ocean to make much difference, so we don't lose any skill from changing to climatology. But we also don't see much loss of skill in weeks 3-4. So everywhere over land where you see stippling, that means there's no difference from the standard forecast. So the only areas that lost skill is this north part of South America and Central Africa. And that's similar here for weeks 5-6 as weeks 3-4. Perhaps there's a little bit more difference in the west coast of the United States in weeks 5-6. But more or less in our suite, the atmosphere is the main driver of surface temperature prediction skill. And here are also the results from the other complementary suites. So as expected, when we initialize all the components with climatology, we get very little skill. But you see there are a few areas when we get to weeks 5-6 that do just as well with climatology as with the standard forecast. And when we only initialize the atmosphere, we get back over a majority of land areas in weeks 3-4, we get back the same thing as the standard forecast. So again, reinforcing the fact that there is largely the atmosphere is contributing in the subseasonal window. And in weeks 5-6, it plays a very large contribution over the land areas. Now, an interesting thing happens when we only run with initializing the land. We do actually get some skill from the model, especially in weeks 1-2 and a little bit in weeks 3-4, especially over South America. So what we think is happening, you actually are seeing coupling here between the land and the atmosphere, which is happening in the absence. So when the atmosphere is not initialized, then it takes a little bit of the memory from the land model and then it gets transferred into the atmosphere through a coupling mechanism. When we only include ocean variability, as we could expect, we don't get much skill until we start getting into weeks 5-6. And primarily we're getting skill from the ocean over in the north part of South America and again, Africa. So those regions keep coming up. So those are, we think, that are largely associated in ENSO, and I'll talk about that for the minute. but you can see that we recover the majority of the skill in these regions just with initializing the ocean. So you don't really need to initialize anything else to get the surface temperature skill in these regions. So we quantify the contribution of ENSO a little more. So what this figure on the right shows is the change in ACC of 2 meter temperature between the active and the neutral ENSO years. And as expected, these are the regions where you're seeing the influence. So north part of South America, Central Africa, and perhaps a little bit on the west coast of the United States, which is what you would expect from teleconnections. But the changes are not large. They're not very large, but in those regions, and so does make a difference. And one thing I forgot to mention, and I'm mainly showing you annual means, we have looked at DJF, we have looked at JJA, but more or less the picture looks the same. All right, so the last thing we've done, and we've struggled how to demonstrate this really well. So this is our, I think, last final attempt. But what we've tried to separate is the contributions for the variability of the different components. I call those VATM, VLAND, VOcean. Every one of the experimental suites also has a contribution from climatology. That's just something we cannot take out. If you're going to initialize the model with something, there's going to be a contribution from climatology. And then we think then there's 3 terms that make a difference: coupling from the atmosphere and the land, coupling from the atmosphere and the ocean. And there might be coupling between land and the ocean, but it should be very small for 2 meter temperature over land. So for the rest of the presentation, we assume that is 0. So for example, our Clima ATM suite will have contributions from climatology, variability of the land, variability of the ocean, and from these coupling terms. So based on all the forecast suites, we can calculate different terms, and we can see if the combination of skill if the total skill is a combination of these individual components. So the ACC in the standard simulation is the ACC of all of these terms combined together. So if the linearity would hold, we could calculate the ACC sum as the ACC from climatology, from atmospheric variability, land, and coupling terms, and so on. So we can do a little bit of math from all these different reforecast sets, and, for example, derive the ACC from the variability of the atmosphere. And we do that by subtracting the ACC from the standard reforecast suite and minus the Clima ATM. And similarly, you can do a little bit more math that Sasha mainly has done, and you can calculate also then the contributions from these coupling terms. So if you see that this is the reason why we needed to run the Clima all suite, because otherwise we couldn't derive those numbers. So I'm sorry if the math is a little bit too much here, but the picture will make things a little clearer. So what you're showing here, and we'll focus on this top left panel, which is the global mean. The yellow is the contribution from the atmosphere. So this is the ACC from variability from the atmosphere. And as you saw earlier, it peaks in the early weeks, and it's still the dominant term in weeks 3, 4. And by the time we get to weeks 5, 6, it's right on par with the ocean, which is the blue line here. As was clear earlier, the land does not contribute much. So our green line here, the contribution from the land is just flat. And again, we think that maybe has to do with just how the coupling is set between land and the atmosphere. And then there is this contribution in this green line, is this coupling between the atmosphere and the land. So that primarily comes up when we don't initialize the atmosphere, then the surface temperature is going to be driven by what the land is doing. And finally, in this pink line here is the sum of all of these terms. So if you add up the yellow, all the solid lines and all the dashed lines together, they do add up to the pink. And what you see is that almost is perfectly the same thing as what you get with the standard reforecast. So the linearity assumption holds everywhere except for this region of South America. So if you look at all the other diagrams, we can add up individual contributions, but there's something different going over South America. And we've seen it in the diagrams, right? So the atmospheric initial condition does not give you as much skill as in other areas, and the ocean and the land atmosphere interactions become important almost from the beginning. So I think that has to do something with the vegetation with this region, different meteorology that happens in that region. But mostly the linearity assumption holds. And we only talked about 2-meter temperature, but we've done all of these figures for precipitation as well. And as you see in this top right figure, this is the ACC for precipitation over land. And it has a very sharp decline, and the scale in the subseasonal window is very low. So these other panels, H through N, are only zooming in on weeks 3 through 6. But you see a very similar message that the atmosphere throughout the subseasonal week 3-4 window is the dominant source of predictability. And then the ocean and the land play a very minor role. However, the ocean starts being on par or greater than the atmosphere when we get to weeks 5-6. And again, with the exception of South America, where the ocean plays a much larger role, and then also Southeast Asia and Australia, where the ocean also is playing a much larger role. And all the terms that we calculated from the Reese forecast suites do add up pretty well to the standard forecast. So that's pretty cool. Okay, so in short, our results suggest that the atmospheric initial state is the dominant source of 2-meter air temperature predictability through weeks 3-4 for the majority of the land areas. Unfortunately, the land initial condition plays a small role, and we're still investigating this a little bit. So Sanjeev, I think the next talk is going to talk about soil moisture prediction in these runs, and we're looking into the reasons why this is happening, but likely we're just not getting the benefit from the coupling in our system. So predictability from the ocean initial state exceeds that from the atmosphere only after 4 weeks. And we don't have the restarts for these simulations in order to bring them out a little further in time to see when really the ocean would be playing a larger role. But the ocean does play a larger role during the active ENSO years. And for the precipitation scale, again, the atmospheric initial state is the main driver, except for these regions of South America and Southeast Asia and Australia. All right, and lastly, so the data is already on the Climate Data Gateway. If you would like to look at these reforecast suites, they are also in Casper in this directory, and we're just folding them under this common DOI for all the S2S reforecast suites. But if you follow that link, then there it is. There's all the, and basically we have the P1 variables, which is just following the SubX protocol, surface temperature, etc. But if you need additional variables, please go ahead and ask. We probably do have them. All right, so thank you, and I'll take any questions.
Questions for Yaga? Judith?
Hi, Yaga. Thanks so much. Very interesting. I have 2 quick questions. One of them is, why do you have so low skill from the atmospheric component until week 1? Does it have to do with the verification being different from the initialization? Is there a spin-up problem? And the other one was a comprehension question. These first ACCs on your first slide, is this done against a verification data set like ALPS, or is this done in the perfect model world?
Okay, so I'll answer the second question. So these are, we've done this against the CPC data, and we've done it against ERA interim. I'm showing you ERA interim because we also wanted to see what happens on the oceans, because when we're showing the CPC data, people would kept asking what's going on over the oceans, but it doesn't really make much difference. And I'm not sure if I understood your first question. So the standard reforecast suite, so the ACC values are pretty close to 1 in the weeks 1-2, but they're, here, this one shows it a little clearer. So they're pretty close to 1. They're not, they're little, there is a little shock of the system, so they're not as high as ECMWF, but they're, I think, pretty well as expected. Maybe I didn't understand the question.
Yeah, I was asking about the line plots that you showed for, like the last slides you showed.
Oh, okay.
Where you do the sum. Yeah, those ones.
Yes.
I'm surprised that the atmosphere peaks at week 1 rather than before.
Oh, I see what you're saying. So I think that is due to the initialization shock a little bit in the beginning. So that's why there is, I think, we get in the first couple of days, we don't get as much benefit as we could. And I think there is also then these interactions with the land model. So there's something we don't fully understand in the time period.
Thanks.
Yep.
Matt?
Yeah, I was just curious, when you look at the runs where you turn off where you don't put in an ocean initialization, what's happening to say, the ensotropical convection signal? Presumably that's not just dying, is it? Is it got some tail? Is that tail long enough that you're still seeing the effect to the ocean, even though you don't have it explicitly?
So in which one of these suites?
When you're not initializing with the ocean.
Okay.
So you don't have ENSO, right? I assume.
Yes, so you see that in the drop in skill over the ocean. So that's partly why we're showing that. So yes, so in this Klima Ocean suite, if you compare, for example, week 3-4, what's going on with the ocean, then compare that to the standard reforecast. So you see the drop of in skill over the ocean regions, right? So no, there is no ENSO at all in these.
Right, but what would vary that? I guess I'm just wondering what happens to how long it takes for the entire atmosphere to forget about the ENSO, the SST anomaly.
So that's a good question because the atmosphere is initialized with a state that's consistent with the ENSO at the time of initialization.
Right.
We don't have it.
Yeah, that's my point.
Yeah, so this is partly where we could be getting in that region in South America still the benefit of that ENSO signal being in the atmosphere. But we can't, yeah, I don't know how to separate that. I would imagine the atmosphere forgets about it pretty quickly, but.
It would be good to check.
Yeah.
Yeah, I think in the interest of time, we should move on to our next speaker, and you can follow up with Yaga on the chat. So Eniola Olanian, I think, is ready and able to present.
Okay, if you can hear me or see me.
Yes, we can.
Yes, good evening from Nigeria. And I am going to talk on the performance evaluation of real-time subseasonal rainfall forecast over West Africa of 2000 and 2001 monsoon season for operational use. This is a fallout from a research collaboration called the GCRF African Swift from 2017 to 2022. It gives us the that leverage to access the ECMWF forecast in real time during the real-time pilot project. So the basic aim. Oh, Jesus, it's not going. Ah, oh, sorry. Okay, it's going. Now the basic aim of this work is to have a scientific understanding of the S2S prediction system in West Africa, the one that is required to provide real-time forecast operationally. And the objective here is to access the performance of the rainfall forecast from the S2S over West Africa in order for us to have improved knowledge on how this model represents the monsoon dynamics. So therefore, we want to know what is the skill of this S2S prediction system in producing monsoon evolution in real time. What is the skill of this S2S in predicting rainfall climatology and its variability on the fly? And if we have the evaluation of this S2S model, is it sensitive to observational uncertainty? So here for this experiment, we use the ECMWF S2S rainfall data in real time of 2020 and 2021. The date of initialization here is from March to October of that same year. And the ICAST from on the fly from 2001 to 2019 to test the sensitivity of this evaluation to the observation. We use the GPM IMAG and TAMSAT for the same period. So in effect, we have in every year 15 start dates. And for each start dates of every year, we have 4 lead times decadally, that is in 10 days time advance. So again, we now classify the start dates into season, so into 4 seasons. So we have the season from March to April, which we call the pre-monsoon season, and May to June, July to August, which we call northern monsoon peak, and from September to October, which we call the second southern monsoon peak. So we want to set the attributes of this the focus quality of this S2S. So in order for us to evaluate this, we use the deterministic and probabilistic techniques. So the deterministic evaluation techniques that we use consist of the bias, anomaly, synchronization, and linear correlation. And while the probabilistic evaluation used here is the RAM probability score to test the reliability from 4 rainfall threshold and the relative operative characteristics to see the separability of the model. So in order for us to be explicit in the way we compute the association in terms of correlation, we compute the correlation from all start dates from each lead time, which we call the spatiotemporal, and from each lead time from each start date, which we call the spatial. Then we computed from the spatiotemporal the correlation of all lead times from all start dates. Then from the spatial, we computed from the mean correlation for each lead time from all start dates and for all lead time from all start dates. So the RAM probability score is computed for each lead time from all start dates and for all lead time from each start dates. And lastly, the ROC is computed for all lead times from all start dates in the ICAST. So later, based on common climatology, we classified West Africa into 4 regions, which is the Gulf of Guinea, the Guinea Forest, the Sudan, and the Sahel. The first map that I'm going to be showing here is the eyeball verification that any forecaster wants to see. And this is showing the probability forecast from the S2S and the observed decadal rainfall accumulation of less than 10 millimeters. So what we want to see here, I don't know if you can see this, but you can. I don't know. What we want to see here is the ability of the model to produce low rainfall. And we can see from the upper panel, I don't know if I go here, we can see from the upper panel here that the model captures the little dry season over the Gulf of Guinea and its reduction in 2001. So the second map is showing the same thing, but of rainfall that is greater than 100 mm. This is just to show how well the model captured the evolution of the monsoon. And we can see that if we compare the GPM observation to the forecast here, the model can capture, it's able to capture the bimodal characteristics in the south and the unimodal characteristics in the north. So the next one is showing the bias of the model. Climatologically, in the ICAST, we can see that the model is wetter during July and August period in the south and drier in the north during the same period. And this is more detailed in 2001 and 2002. I do not want to dwell on the TAMSAT. If you can see the TAMSAT on the right hand side, then it's just to compare how the model behaves using TAMSAT and using GPM. But I'm not going to dwell on TAMSAT. So this is showing the distribution of interannual variability of the standardized decadal rainfall anomaly of the model. And here, the model ensemble mean is the solid black line. The red boxes are from the GPM observation, and the green one are from the time set. We could see here that the model, irrespective of the time of the lead time and irrespective of the area, it can produce the interannual variability for all the lead time, for any lead time that is on the subject. So this I won't talk about, is just to give credence to the kind of outlier that we have here in the time set. So it's just a way of giving credence to the model, considering the sign alone and not the magnitude and sign. So this here is the correlation between the ensemble mean of the model and the GPM for all lead time, for all start date and all lead time. And you can see that consistently the anomaly has the weakest scale in correlation, although it increases from the Gulf of Guinea, the region 1 to region 4. But seasonally, we could see a sharp drop in scale during the peak of the non-stem monsoon, for the fact that again the strongest scale is the ICAS is in the ICAS, and the lowest scale is in the anomaly. I won't talk about the spatial, it's just to compare those ones. So this is the correlation scale of the model from all lead time, from each lead time of all start dates. And what this is signifying is to see at what lead time do we have the strongest scale. And even as the region 1 has the lowest correlation scale, it does not imply that the last lead time has the lowest scale. So I am going to the round probability score here. The first thing that strikes is the fact that the ability of the model to forecast the ranges of events is small during the northern monsoon peak, and that the lowest scale here is in the Sahel. Again, though in 2001 in region 4 with the lowest scale, there is this systematic decrease of scale from lead 1 to lead 4, but it is not consistent in all, even while it is consistent that the Sahel has the lowest scale and the Gulf of Guinea has the strongest scale. So this is showing the rock, which is to indicate the separability of the model. And we can see here that the model has no scale in discriminating low rainfall over the Gulf of Guinea and heavy rainfall over the Sahel, despite the fact that in detecting rainfall anomalies, it displays strongest scale over the Sahel, as can be seen in here. So, in summary, we have seen that the model, the SQS model, could capture the evolution of the monsoon, which includes the dryness, the wetness, and the monsoon jump. It shows that during the northern monsoon peak, the model is generally wetter in the south and drier in the north, with different attributes using time series. We can also see that the decrease or increase of correlation scale across lead times over all regions is not consistent. So again, the correlation scale in the spatial compared to the spatial temporal is stronger. It also shows here that the model could predict on the average 8 correct rainfall anomaly forecasts out of 10 across region, regardless of the lead time. The RPPSS generally decrease towards the Sahel, but weakest over the Gulf of Guinea in the time set. It also revealed significant inconsistency in rank probability score across lead time from all start dates. It's with area under curve of about 0.78, the model ability to discriminate different rainfall thresholds across all regions is strong. And finally, we have seen that the results have shown us that the assessment of the skill in this model is sensitive to the uncertainties in the validating observations. So I will stop here because of, thank you for listening, and I'm going to welcome any additional advice and question. Thank you so much.
Maybe we can take one question while we're transitioning to the next speaker. Yeah, Yana.
Oh, sorry, I apologize. Sorry.
Thanks, Eniol. I think people can follow in chat, and we'll move on to Yanan Duan.
Hello everyone. Our main research result is the land initializations contribute most to the subseasonal soil moisture forecast scale in the US. We thanks to the USDA grant for supporting our research, and we thanks to in the CESM to sub-X sensitivity experiment data. The motivation of our study is the soil moisture. Sorry. Oh, it worked. Thank you. The motivation of our study is the soil moisture predictability related questions. The first question we want to see, can we predict root zone soil moisture anomalies weeks to months in advance? And based on our previous study, we found that the soil moisture has significant predictability from seasonal to decadal timescales, even with limited precipitation predictability. We want to know which sources contribute most to the soil moisture predictability, like the atmosphere, ocean, and land. The model we use is subseasonal forecast experiment, the sub-X CESM2 large ensemble. It has one control experiment, and we use another 4 sensitivity experiments. Just like the introduction in Dr. Yaga presentation, we use the different initial states. For example, the land-only experiment we only have the realistic land initialization. For the atmosphere and ocean, the model has the climatology instead of the realistic initial states. And for the control experiment, we have all the 3, the atmosphere, ocean, aligned realistic initial states. For the model experiment details, like the initialization data site, it should be the reanalysis data site, and for the reforecast period, it is the same. And the ensemble size, real-time forecast of them were introduced in the Dr. Yaga presentation. The study scale in our study is from the surface to 0.5 meter root zone soil moisture. To remove the drift, we normalized the soil moisture for each point, for each forecast initial week, and for each month, and also across the forecast late from the 0 to 45 days. And to remove the biases in observation, we calculate the average of the 4 soil moisture observation sources. They are remote sensing and real analysis based soil moisture. the ERE5 line, submerge, gleam, and mirror to soil moisture. We calculate for 15 days moving average along the forecast lay days from the 0 to 45. So we don't have the first 7 days and last 7 days soil moisture due to the running average. We select the subseasonal scale. It is the week 3 to 4 forecast. And because it is also the gap between the short-term weather forecast and the long-term seasonal outlook, we want to test the model performance during that window. The first result from our study is a comparison within the 4 observation day set. The first column is ERV5, the second is submerge, the third is gleam, and the fourth is mirror 2. The forecast scale is weakest during ERE5 and highest for mirror 2. So we combine them together, calculate the average, normalize the observation soil moisture, and calculate the anomaly correlation between the observation and the CESM to large ensemble soil moisture. The second result from our study is the forecast scale in the 3 experiments. The left column is the control experiment. The middle is ocean line experiment. The third column is land-only realistic initial states experiment. We find the very limited difference within the 3 columns. By that means the land shows the highest contribution to the soil moisture predictability during the subseasonal time scale. To make the result much more straightforward, we show the relative contribution from the 3 sources by the area ratio. The region we select is the neon region 6, which is the agriculturally dominated ecoregion. The left figure, y-axis is model observation correlation, and the x-axis is the forecast late from the 8 to 38 days. Due to the moving average, we don't have the first 7 days and the last 7 days soil moisture. The right line, the right solid line is from the land-only experiment, and the blue line is from ocean line in a realistic initial states experiment. The blank line is from control experiment. So the 19% of the total predictability is coming from the land sources, land initializations, and the ocean only contribute 1%. It's worth to note that the light blue line is from the difference between the ocean line experiment and the land experiment. It is similar for the gray region. The atmosphere 9% is from the difference between the control experiment and ocean line experiment. To test if the result is robust or not, we also study the one source only sub-X experiment to see if our result is robust or not. Because in the former slide, it is a difference. Here we use the land only, ocean only, and atmosphere only to see if the land also contribute most to the soil moisture predictability. We find that for the subseasonal time scale, the land contribute highest to the soil moisture predictability. For the ocean, there's very limited scale during the fall season, and the atmosphere has significant contribution in the spring season. The dotted region is the correlation where it is significant with the 0.05 significant level. So the implication of this result is that we should use observationally constrained land initialization to improve the forecast scale, especially in the agricultural region. We also compare the 2-meter surface air temperature and soil moisture result in the sub-X. We find that the atmosphere contributes most to the near surface air temperature in the CESM to large ensemble experiments. The atmosphere has limited contribution, but the ocean has limited contributions. The atmosphere has significant contribution during the fall season, SON season. To make the result much more straightforward. We also plot relatively area to compare the predictability from the three sources. The left figure is the soil moisture, right is 2 meter air temperature. It is also in the neon-recall region 6. We find that the land contribution decreased from the 90% to the 44%. The atmosphere contribution increased from 9% to 49%. The ocean contributes 7% in the air temperature predictability. Also, the light blue and light gray region is the model difference. Oh, here's the actual slide, which shows the 2 meter surface temperature predictability during the week 1 and 2. Thank you.
Questions?
So are these results in agreement with Yaga's results, that these maps? I feel like you have more skill from the land.
For this figure, it is similar.
Okay.
For this figure, this figure, because we show the difference between the experiment, if we add the one source on the experiment forecast scale together, it will be much more greater than, for example, the control experiment. If we add the land, atmosphere, and ocean one source experiment predictability scale together, it will be much greater than this solid line. So by that means, for the soil moisture predictability, it has non-linearity in the model scale, which is different from the air temperature predictability.
Nice talk. I just had a quick question. Did you compare your soil moisture to persistence or damped persistence, depending on your metric?
No, it would be a good research orientation.
Yeah, I mean, I think that would be a good baseline in your case, because that's kind of the immediate question here is, are you basically seeing the soil, whatever initialization you have, just kind of damping away, and it's just there's a lot of memory in the land, so it takes a while? Or is it doing something else?
Oh, yeah. I have not shown the result yet. I'm working on the soil moisture memory. We want to remove it and see how much the predictability is.
I'm sorry, I can't hear you.
Battery go? Oh, it works. That is the work I'm working now on. We want to remove the soil moisture memory from the model forecast scale and see how much the forecast scale from the model initial state itself, or from the model itself, or from the soil moisture memory directly, because the memory has a very significant effect on the predictability, even for the decadal time scale. So, yeah, that is the figure I'm working on now. It still has some script problems, so yeah. Thank you very much.
One last question.
Go ahead. Thank you, great talk. A quick question, have you checked the surface layer soil moisture?
Oh, not yet.
Oh.
Yeah.
We should expect. Or if surface layer soil moisture?
Yeah, the surface layer, with my limited experience, it was influenced by the atmosphere, especially the precipitation significantly. So the land atmosphere coupling effect will play a larger role in the surface layer. Oh, and yeah, it would be a great point. Since the SMAP R4 soil moisture is the surface layer, it is 0.05 meters. So it would be if we had time, we will have a look on it to make the research more integral. Thank you.
Thanks very much. We'll move on to Judith Berner.
Do you want me to go fast? Or?
Up to you.
Right underneath. Thanks. Thank you so much. I'm going to report on the impact of the stochastic parameterizations on the S2S timescale in coupled simulations with CESM. So the idea for stochastic parameterizations is that especially as resolution increases, the classical bulk assumptions no longer hold, and we want to actually represent the subgrid scale state. We want to sample the subgrid scale state rather than look at its mean. This is very loud. Can I put this a little down? One widely used scheme is this SPPT scheme, which is the stochastically perturbed physics tendency scheme, where the parameterized tendencies from the physics, where the accumulated tendencies from the physical parameterizations are perturbed with a random field. So, and this random field has temporal and spatial correlations. So this is a simple equation. It's the update. The tendency is decomposed in the dynamical tendencies from the dicore and the physical parameterizations, and we perturb them with R+1. So these are Gaussian perturbations at each grid point, but adjacent grid points are correlated. The scheme perturbs the accumulated tendencies from U, V, T, and Q. And in particular, we do not perturb the radiative tendencies because for those, it has been shown that those perturbations shouldn't be Gaussian from coarse-graining experiments. I will, in the interest of time, I will skip over this, but we need to make sure that if we perturb Q, that moisture is preserved. And so we actually have to perturb also the P minus E term, which is not so easy in CESM because half of the parameterization schemes are executed before the coupling and half of them later. So if you perturb at the end of the physics time step, we need to save that pattern, and then we compute a precipitation correction, which is then added on half a time step later. And in the climatological runs, that causes some issues with RESTOM that we're currently working on with the top of the atmosphere energy balance. Here I'm going to talk about coupled simulations. So this is following, this is the suite that Yaga developed, the S2S suite. We're using CSM2. And then we're using Yaga's run as our control simulation, and we compare that to a simulation where we add the stochastic scheme. First of all, I looked at perfect model skill. So this is where you verify the model not against observations, but against an ensemble member. And you have to do this carefully to get the theoretical results. For example, you need to compute the ensemble mean based on all ensemble members, including the verifying member, to get some of the theoretical results that are valid in the perfect model scenarios. I show here the same format throughout the slides. Weeks 1, 2 are on the left, weeks 3, 4 in the middle, and weeks 5, 6 on the right side. And I'm comparing here ECMWF to CSM2. And if we look here at weeks 3, 4, we see that in the perfect model world, CSM2 actually has more, predicts more skill than ECMWF. So the intrinsic predictability of CSM2 is higher than that of ECMWF. So this is a model difference. And you can see this, goes all the way out to weeks 5, 6. And we see some of these hotspots that also Yaga showed, which is basically the tropical belt. Now we're looking at actual model skill. So now we're verifying against observations. And if you look very carefully, we're seeing two things. First of all, I was really impressed to see that the CSM model skill on the subseasonal time scale out to weeks 5, 6 is very similar to that of ECMWF. So it means that the initializations that the ECMWF does, at least in weeks, after week 2, 3, are not the leading cause for model skill. Secondly, we see that now CSM actually has less skill a little bit than ECMWF. And so this perfect model skill did not translate into actual skill. The perfect model skill is often looked at the predictable horizon. So this is, if we cannot, a model has no perfect model skill, we would it not to expect to have the process. So if a process has no skill, then we would not expect this in actual verification. Here's a signal to noise paradox. So here I'm comparing the actual model skill to the perfect model skill. And even on a sub-seasonal time scale, we get these regions in ECMWF, if you see at the top, where the actual hindcast skill is higher than that of the perfect model. And this has been reported on longer time scales from seasonal to decadal, and is the role of active research. We also note that CSM doesn't have that, and so there could be several reasons for that. It could be that the actual skill is actually smaller than that of ECMWF, or it could be that the perfect model skill is estimated too high. Sorry, I cut that off, but those are differences from what I showed you before. Typically, you want to do ratios for the signal to noise, but then you can divide by 0. So here I'm just going to, it actually doesn't matter because I'm just looking at the differences. Unless you ask about statistical significance, I can come back to that. However, there's another reason. So why is the intrinsic skill of CSM2 higher than that of CSM? And one of the reasons is that there might not be enough spread in those simulations. And so here you look at spread. Here is shown spread error for 2-meter temperature and precip. So the solid bars are the errors, and then the lighter ones, dashed ones, are the spread. And so if you look at ECMWF, really all the models, you see that the spread is always smaller than the error. And this is the original reason why stochastic parameterizations were developed, because having this under-dispersion will really hurt your probabilistic skill scores. And this is why stochastic parameterizations are now routinely used in numerical weather prediction. And if you look, for example, at week 3, 4 for temperature, you see that for CSM, the error, this is global mean errors, went actually up for 2-meter temperature, but the spread is the same. And so that means that the under-dispersion in the CSM runs is worse than those in the ECMWF runs. What we then want to do with the stochastic parameterizations is, ideally, we don't want to increase the error, but we want to increase the spread. That's the holy grail of stochastic parameterizations, and we see we can actually do this for temperature in the subseasonal timescales. It's very small, but we can increase the spread and not increase the RMS error. And in particular for precipitation, we get a very large spread, which actually is now approaching the RMS error. This is now a different format. I'm showing here only weeks 3, 4. On the left side are these perfect model predictions. On the middle one, the actual ones. And then on the hind side, the differences. And here you can see that if we have these stochastic parameterizations, sort of this signal-to-noise paradox, or these regions where the model is actually over-dispersive, is reduced. The regions that pop out are to first order similar than those in ECMWF. So I think from this we can conclude that the perfect model skill in these S2S forecast and CSM2 is over-predicted because the system is under-dispersive. What is now the actual model skill? This is now DJF only because we have these, the stochastic runs are only done for the extended winter season. At the bottom, I show you the difference between SPPT and CSM2. And so to first order, those are very small differences. Where it's blue, SPPT is worse, and where it's red, SPPT is slightly better. But overall, if we take the mean, especially over sort of the northern hemispheric regions, I would say that SPPT degrades. It makes the ACC worse. However, if we look at the RPS of tercile forecasts, the rank probability score is a probabilistic score that doesn't look at the deterministic forecast, but it compares the distribution of forecasts to those of occurrences. We see that ECMWF, we see that SPPT is doing well. So I should say this is the RPS. So this is a negatively oriented score, which means the smaller the better, and a perfect forecast would be 0. And we also have to note this is now shown for weeks 3, 4. So these are actually relatively low overall skills, although I've shown that they were all positive. So I think there is really skill on these time scales, as we all know. And if we now look at this probabilistic skill score, the lower it is, the better. And so to first order, I would also say that if we compare the CSM results, the red bars, to ECMWF, those are worse. But overall, I am over and over really impressed how well CSM does also probabilistically when compared to ECMWF on those S2S timescales. And I think the reason for that is that CSM is really good at capturing internal variability and teleconnections and processes like that. But with the stochastic parameterization, the green bars, we are not only better than CSM2, but also better than ECMWF, so have better probabilistic skill. And the reason for this is that we could pump in a lot of spread in there. This would probably not go through at an operational center because you cannot reduce deterministic skill. So here we are basically trading a little bit of deterministic skill for probabilistic skill. And then in precipitation, the results are similar good. But if you look at this regionally, this improvement comes mostly from the tropics. Finally, we wanted to extend this and look at state dependence. It has been shown that stochastic parameterizations can can have beneficial impacts on models in terms of capturing blocking, such as associated with the NAO and PNA. And so here we wanted to look at state-dependent predictability. This is now only focusing on North America. This is in CSM2. And here I have neutral condition when the initial conditions project on the positive PNA pattern and the negative one. And so the state-dependent predictability tells you that if you project your initial condition is in the positive PNA, then you have wide regions where your S2S predictability, this is 2-meter temperature for weeks 3, 4, are better than those if you look at all states. And also in the negative pattern, so for the positive, you get sort of in the northeast this greatly increased predictability. This is ACC, and in the negative one, it's real all over CONUS. This is the plot for SPPT, and so if anything, there's a small degradation, not really an improvement. So I think the stochastic parameterizations have not improved the state-dependent predictability associated with the PNA. This is ENSO. Again, we're looking at forecast where the initial date is projecting onto positive or negative ENSO states, and we get there this increased predictability in the northeast in week 3, 4. That is part of the classical teleconnections. And if we have the stochastic parameterizations, we don't see a big improvement. And this is my talk. Thank you. Oh, can they see us? Okay.
Go ahead, Matt. Comment and question. The comment was, you might try looking at reliability and sharpness separately, or maybe, I don't know if you have, maybe I should have asked it that way. Have you tried looking at reliability and sharpness separately to see, if your RPS PS is going up, which it's really coming from.
Yeah, I've not done it in those, but I've done this enough in other forecast system. I'm sure it's the reliability, not the sharpness. So if you improve the spread, you automatically improve reliability.
Yeah, I mean, you can go to Climo and you'll improve reliability, but that's...
Right. Now I understand. But and the sharpness, I think if the sharpness would be better, then the ACC would be better. And honestly, so for me, the biggest challenge in this has been the regionality of it, right? If you look at Quebec or the sort of this sort of Labrador region, obviously the teleconnections, they have very different impacts on the different regions, and so there's a lot going on. There's a lot of ways to slice these results.
Okay. And I guess the question I had, which is a little different than what you showed at the end, is, you know, we've been trying to argue that these systems, you should just mainly look at forecasts of opportunity, you know, because if you're just improving low skill from like bad to mediocre, you're not really helping. So have you tried looking at that here, just stratifying cases of high skill, say in the control, and then asking whether you're doing better or worse under those scenarios? I mean, maybe you're improving it and you're making it worse everywhere else, but then who cares?
With the stochastic parameterization?
Well, I mean, maybe you're improving it in the high skill cases, and so the fact that you're making your low skill might be going down, but you don't care because they're not where you're making your money on the forecast anyway.
No, I think this would be interesting to do. I think the idea is that you want to predict when you have extended predictability, and so this is why we do this projection onto the initial state, because we want to say things like, oh, if I project today on the negative PNA, then I think my forecast will be better. So,
Right, but I think in your case, I would just start by asking whether you're making an improvement, because I think it's not an unreasonable assumption to say, I mean, there's some sampling, but obviously, if you look at the entire set of hindcasts and pick out, you know, the highest 10%, for example, when we do this with the limb, what we find is the limb predicts the highest 10% of the IFS. So in a backward sense, I could just take the highest 10% of the IFS, and then say, okay, I think those are high skill events that I should be able to predict, at least in the context of the limb I can. So now I'm just gonna say, let's just pretend those really are, in fact, the most predictable events. Now let's compare those events, you know, the forecasts for those events in the CESM and the CSM SPPT, too many P's in there, T, and see how you're doing in that subset of events.
Yeah. No, I think this is a good idea. Part of why we started this work is that the SPPT improves ENSO variability, but ours is too strong, so it dampens it. And so the hope was that the teleconnection patterns would be better and then be reflected in this improved S2S skill. But yeah, maybe a different slicing would bring some of those improvements up.
I had a quick one, yeah. Have you, or would it be meaningful to compare the SPPT with CESM2 where you've like post-processor bias corrected the ensemble spread with some of those probabilistic metrics? Like I know you wouldn't be capturing the benefits in the physics there, but it might be interesting for how it feeds through to some of the probabilistic metrics.
Yeah, no, I think this is always the question if you're trying to improve your dynamical models or improving forecasts, and you would do this for improving forecasts. I think the idea of where a stochastic scheme would outperform a sophisticated post-processing method or, you know, machine learned ones, etc., is if you really are in if you look at the Lorenz attractor and you sort of have two regimes and you just never get there, and so you never get the evolution right because you never reach that particular one, or if you have two cold SSTs and you never kick off the hurricane. So the idea is that these stochastic schemes do kick the model into phase spaces it wouldn't go otherwise, but should during runtime. I'm sure it would be interesting to compare this, but then the question is, if you both post-process, you know, would the SPPT still be better? Yeah, but I mean, those are interesting questions for applications. Yeah.
Super, thanks, that makes sense.
Yeah. Thanks so much.
Thanks, Judith. One more talk before lunch, Nick Davis.
online, right?
All right, let me know if you all can see that. Okay.
Yeah, we can.
Great, thanks. I'm just going to briefly talk about this month's substratospheric warming and how that has shaped out in the real-time CSM2 forecasts. So I'll just provide a brief picture of what I'm talking about. I think the last few years there's been a lot of news and science about sudden warmings, but Zach Lawrence, who's now at NOAA in Boulder, has a really great website with visualizations of the vortex. So the potential temperature here, you can think of this as pressure surfaces vertically, and so we're going up basically from the lower stratosphere way high up into the upper stratosphere, and these are just some ISO contours chosen to illustrate the vortex. And so on the left was the vortex in early February. It looks like a vortex. It's very circular over the pole, very regularly shaped. And then by February 16th, which was the official date of this year's sudden warming, you can see that the vortex has really displaced and sort of whipsawed off the pole. And then by today, by this morning, the vortex is still in a state of disarray. So basically there's not really any vortex to speak of in the stratosphere right now. And so these occur usually every 2 years or so on average. Just to give you an idea of what the forecasts this year were doing. So there's two forecasts, Wacom and CAM, and this is looking back at our February 6th initialization and then our initialization last week with the verification overlaid in black here. And so the normal diagnostic folks use is 60 north, 10 hectopascal zonal wind. And when that's 0, you call it a sudden warming. And so each of the sort of the lines here is a member that has predicted a sudden warming. And you can see that basically by February 6th, it was pretty much in the cards that we were going to get a sudden warming. So we had something like a 10 plus day lead time. There was actually some visibility on the sudden warming by the second to last week of January, but it just wasn't that convincing. But there were a number of model members predicting one. So like I said, these usually happen every 2 years or so. And this is for the week 3 to 4 forecast anomalies for the run initialized last week. So the temperature anomalies here on the left, and on the right is the sort of standard pattern that we expect after a sudden warming. And so the standard pattern that we expect is sort of cold air over Europe and especially Siberia, warm temperatures over parts of the Middle East and the Mediterranean, warm temperatures over Greenland and Canada and Alaska, and then cold temperatures over the US. So there's commonly cold air outbreaks in the month following a sudden warming. But you can see that that's basically orthogonal to what the model forecast was predicting for the month following the sudden warming. So the obvious question is, what's on the go? And I should say, CSM was not an outlier here. Other sub-X models were predicting this sort of similar pattern on the left. So I'm saying this is not your average sudden warming. And so one of the ways we look at the dynamics and the propagation of sudden warming circulation anomalies is to look at polar cap geopotential height, which is really pretty much the same as the Northern Annular Mode Index. So in this plot, I'm showing on the left the CSM2 Wacom 6 forecasts initialized last week, along with the GFS forecasts initialized at the same date. And so warm colors here mean the same thing on the left and the right. Cool colors mean the same thing. So warm colors mean a warm polar cap. So when there's a sudden warming, we have a really strong warming of the polar cap that tends to descend from the middle to upper stratosphere. What's interesting about this one is if you look at the forecast on the left, especially because we go out a little further, there's no warm polar cap at the surface really to speak of. We've basically got a cold polar cap, which is giving you those sort of opposite sign temperature anomalies that you expect. And GFS seemed to be consistent with CSM. So the question is, does that mean there's no coupling with this between the sudden warming and the surface? I'll talk about that in a second, but as I toggle back and forth here, you can see that at some point last week, GFS started to hint at, again, this negative surface NAM that we usually expect after sudden warming, that's coinciding with this sort of second disruption around March 1st that was forecast. And then if I toggle forward again, yesterday, GFS backed off from this sort of negative NAM at the surface. But what's interesting now is CSM has converged with GFS on this second anomaly, basically on March 1st, an apparent downward propagation of that anomaly, and then a sort of warm polar cap negative NAM at the surface sometime in mid-March. And so the two models were a little bit different. CSM didn't want that second disruption. GFS wanted more coupling with the surface, but they've now sort of converged. And the question is this a non-coupling sudden stratospheric warming? And I think actually the answer is no, but maybe it's just in a different way than we usually expect. Usually we expect to see the warm polar cap. But if I take those February 13th forecasts and sort of split them into ones with an SSW and ones without an SSW, the ones without an SSW had a much colder polar cap in the forecast than you otherwise would expect. And so basically the perspective I'd advocate is, just because you don't see the same signed NAM anomaly at the surface, does not mean that that the sudden warming is not associated with a shift in surface weather conditions. And so the polar cap would be colder, and our temperatures in the mid latitudes would probably be even milder if the sudden warming had not occurred, or at least co-occurred. And so one thing we can do is regress this index, the polar cap geopotential height anomaly, on the strength of, on the left, the sudden warming, and then on the right, the secondary disruption. And you can see that when we get a stronger sudden warming in the forecast, or we get a stronger secondary disruption, we get this sort of elevated, and I should say warmer polar cap at the surface. And so basically, if you just look at the shift in the polar cap conditions, you see a pretty good reflection of the surface and the stratospheric coupled variability. And that's sort of all I had. I wanted to just give an update and show kind of some of the predictive skill of CSM for this event, but also show that, just because sudden warmings don't look like the normal composite doesn't necessarily mean that they're not coupling with the surface. Thanks.
Questions for Nick?
I'm just wondering what your view is on the links with cold air outbreaks. I mean, I feel like people often, they happen just after a sudden warming, but they just happen also in winter, and we're very cold right now. I mean, do you think how much, I guess, variance of those kind of events do you think is explained by the sudden warmings?
Yeah, it's hard. I know you get into a definitional problem. Like, we're cold now, but I think most folks, when they're talking about cold air outbreaks, are talking, I think the indices are like a certain number of days below a certain threshold. So like 2021, when we had like a week where we barely punched above zero, that's definitely a cold air outbreak. Like the odd day or two when a shore wave comes through and dumps snow, I don't know how that gets classified, but yeah, I think the trouble is the smaller scale the event in time and space, probably the harder it is to draw the connection to the sudden warming. So for sure, like when we're saying we don't see the normal surface impacts here, we're talking like 2-week averages. So I know there's a few folks with papers looking at now more of this shift in distributions, which is doing a better job of recognizing that, it's not just it's not like the ENSO composite. You know, it's like we're going through the same thing where everyone would say, oh, it's ENSO, so that means the snow is going to do this. Well, it's kind of like a shift to distribution. So I think there's work showing that it shifts to distributions now, but yeah, the like you said, there's colder outbreaks whether there's a sudden warming or not. So obviously they're not the ultimate cause necessarily.
Thanks. Yeah. So we have a question online from John Albers. He asks, are you concerned that you are over-interpreting the drips in the troposphere? That is, the stratospheric coupling effect is inherently weak and is easy to cover via other processes. Internal variability in the troposphere dominates in terms of power, so just looking at a dripping paint plot may not tell you much about whether you have coupling or not.
Yeah, I mean, I think the dripping paint is like a zero order perspective. The only reason I wanted to show this is just to like highlight the dripping paint on their own. I think when folks just do an absolute composite, and by the way, I should say, I don't actually view this as downward impacts. I think we had a paper last year in Nature Comms that, yeah, basically, I think this is two-way coupling if there is coupling. And how you deal with internal variability here, I mean, I don't know, I guess one way to do it is to take the members without a sudden warming and look at how things have shifted, although you can see there's not a great sample. I think if you view it as coupling, like not just pure downward, I think, you know, maybe there's something useful to the polar cap geopotential height anomalies. I will say I'm really careful here to say it's not downward. Just that when we've got a stronger sudden warming or a stronger disruption across these model runs, we seem to have a more positive polar cap geopotential height at the surface. That could very well mean that the dynamics of the surface are actually the things governing the polar cap geopotential height at, you know, the lower stratosphere. It could be a really strong upward effect. Yeah, I'm not going to comment on which direction everything is going. Cool.
Just a comment, I just note that there's a reasonably strong La Nina going on now, and the warming in the Northeast is very much a La Nina sort of signature with cooling in the West. And I know when we sit in on the weekly weeks 3-4 CPC discussions, and certainly for this period, they've been focusing on questions of a fairly strong MJO also propagating through along with the La Nina. So there may be other things going on here as well. And it may just be that the stratospheric effect is there and it's just being entirely masked in this instance by what's going on in the tropics.
Right, so you're sort of, yeah, pointing to this warm blob over the Northeast and the sort of Great Lakes. Yeah, I mean, I think that was my goal with this, is to just say that, yes, just because we don't see the usual suspects of like sudden warmings where you get this positive polar cap height at the surface, that doesn't mean there's some kind of association going on behind the scenes. Yeah, I agree. I mean, when you get down to individual events, you've got a really difficult bag of things to tease apart. But I think just to address both the previous questions, yeah, I think at least when we look at the relationship between polar cap heights and the severity of what's going on in the stratosphere, we see evidence that there's an association, regardless of the actual values at the surface. So yeah, I agree. There's a lot going on. Thanks, great questions.
I think that wraps it. Let's thank all our speakers again from the morning. We'll reconvene at 1:15. wait to get a thumbs up from the booth. Okay, Jerry, whenever you're ready.
Okay. So can you hear me okay?
Yes, we can. Thank you.
Okay, good. All right. So I wanted to start out by acknowledging collaborators Ben, Sasha, Yaga, Nan, and Steve. And we're going to be talking about at least two of the challenges in decadal climate prediction. One involves how you initialize the model to do your hindcasts, and then the other is how you remove the drift away from that initial state as you're running your hindcasts. And you have to remove this drift, which is a product of model error, as the model is drifting toward its systematic error state. And you have to remove that drift to calculate anomalies to compare to observations. So the usual thing is you run a very large set of initialized hindcasts with a lot of ensemble members to evaluate skill in the hindcast. So the DPLE has 64 start years and 40 member ensembles for each start year. But of course, that is very expensive and it's very difficult to do. And it's rarely that is there enough computer time available to do such a large set of initialized hindcasts. And of course, the reason you want to do this is you want to have enough samples of start years and drifted hindcasts to form a drifted climatology from which to compute anomalies to compare to observations to quantify the skill of hindcasts. So one of the things we're going to be looking at is it possible to run a smaller number of start years for hindcasts? For example, if you want to do sensitivity experiments or test the model out, or maybe look at case studies, and maybe use the uninitialized free-running historical simulations to form the model climatologies to compute these anomalies and remove the drift. And the reason we think that could be a possibility is looking at a plot like this in the upper right. This is from the DPLE. This is globally average surface temperatures. The black line is the observations representing kind of the initial states. The dots are the successive forecast years as the hindcasts run, the ensemble averages of the 40 ensemble members. And going from blue to red, you can see they go from year 1 to year 10. And you can see right away that the drifts are very large and very rapid away from this observed initial state. But they do kind of converge down here on this kind of green line with the shading around it. And this is the CSM1 large ensemble, the free running uninitialized large ensemble. And so maybe after about lead year 3 or 4, you may be close enough to the systematic error state of the model represented by the large ensemble that you could use that as your climatology to form your anomalies. So how you form these anomalies, there's a number of ways that have been tried. The usual way here is, and used for decade, the S2D as well as seasonal linear annual and S2S, is you take forecast year differences from a model climatologies. In other words, if you're going to look at lead years 3 to 5 for your predictions, you take your whole hindcast data set, look at all drifted 3 to 5 year hindcasts, average those all together to form your drifted model climatology for that time frame, and then you use that as your reference to calculate the anomalies of your hindcast you're going to evaluate. The problem with that is, and you can see it in this plot here, is that the trends over these long time periods that you have your hindcast data sets may be different. So the trend in the initial states, you can see by eye, is different than the trend in the drifted hindcast. So you can introduce problems when you average over the drifted states over this whole time period, especially if you're near the beginning or near the end of hindcast you're trying to evaluate. Another method is you calculate the mean drift and then remove that mean drift from each hindcast and compare that to the observations directly. The problem with that is you can get either enhanced or reduced skill depending on how the low frequency variability is happening in the observations on timescales greater than 15 years. Or you can do kind of a compromise between the first two and forecast your differences from just the previous 15 years of the drifted model hindcast states. So that removes the problem of introducing problems with trends in your drifted hindcasts, and it does kind of put you closer to a previous period that you may want to compare what's different in their predicted period compared to a recent period. And the last one here is one I'm not going to talk about today. So what do these look like? This is an example from the DPLE. This is where we took the initialized state in year 2013, looking at lead years 3 to 7, in other words, the average of years 2015 to 2019, the prediction over that time period. And these are the three methods I was just talking about of removing, forming the climatologies and removing the drift. So this is using the entire drifted hindcast time period to form the drifted climatology and calculates the anomalies. And this is the observed verification using that same method. This is using the previous 15 years of the drifted climatologies and the similar model verification data calculated in the same way. And this is using the bias adjusted drifts compared to observations and compared to the same kind of thing. You can see these are I'll give you somewhat different results. The sense of the result's the same because we wanted to see if the DPLE could predict a transition from negative IPO to positive IPO, and all these three show some evidence of a positive phase of the IPO in this prediction compared to the observations that show a similar kind of thing with some element of a positive IPO compared to persistence, which is quite different. This is just persisting the previous negative phase of the IPO into this prediction period. But in terms of the trends, comparing these two especially, you can see that almost all these anomalies are positive, and this is because of the problems of the different trends. And you have a trend in the data of your drifted hindcasts, and you're looking in this case in the latter part of the period when there's been warming that's occurred, almost you get a part of that warming trend is introduced into your anomaly field. If you take the previous 15 years, you don't have that big trend, and you do get some areas of these negative anomalies that show up in the observations. So that's kind of some of the issues with just how you calculate the anomalies. But then we can also see if the initialization scheme makes a difference. If you have a small number of start years and you use the uninitialized historical large ensemble to form the model climatologies to compute anomalies to evaluate skill of IPO predictions. So what we're going to do is we're going to take two models with two initialization methods. We're going to take the CESM1 and the E3SM-V1. These are the 1 degree or standard resolution versions of these models. And the main difference between these two models is in the ocean component. CSM1 has a version of POP, E3SM-V1 has the MPAS ocean. And we're going to use two different initialization schemes. One is the so-called forced ocean sea ice or FOSSE method, which we've been using at NCAR for quite a long time now. And you run the model, for example, through 5 cycles of 20th and 21st century climate. You use observed forcing from the atmosphere. And as you run through each cycle of the 20th and 21st century, you imprint more of the observed atmospheric forcing on the ocean. And so by the time you get to the 5th cycle, you say, okay, that's going to be our ocean initial states for our hindcast. The other method is the so-called brute force method that Ben Kurtman has been using. And this is pretty simple because you just take the observed reanalysis products from ocean, atmosphere, and land and just interpolate that to the model grid. And those are your initial states. And so we've got a kind of a smaller number of start years every 5 years, starting in 1985, going out to 2015, and then 2016, 2017, and 2018. We have mostly 5 ensemble members for each, except for 3 ensemble members for a couple of the E3SM cases. So what do these drifts look like in terms of drifting away from the initial state? And these are anomalies now taken from the observed initial state. These are the 2 models with the 2 initialization methods, and this is the first month. So you start the models in November 1st, take the average of November, so that's the first month the model is run. You can see that the brute force methods have already drifted a little bit away from the initial state, because by definition their initial state was the observations. But these errors of maybe a 1/10 or 2 are less than in the FOSSI, the models with using the FOSSI method, because the FOSSI method doesn't guarantee that your ocean initial state is exactly what the observations are. It's going to be some distance away from the observations, because you're only using the atmospheric forcing to give you the ocean initial state. You're not nudging the SSTs toward observations. But by the end of year 1, now this is the forecast year 1, and you can see patterns starting to develop in all 4 of these, with these 2 models and the 2 initialization methods. And this pattern is pretty stable. And so you can see that even by year 1, the model has already approached its systematic error state with this pattern of anomalies. And by year 5, you can see that you can't see much difference between the year 3 and the year 5 anomaly patterns. They're a little bit bigger in terms of amplitude, but pretty much the same pattern. And you compare that to the patterns of the historical large ensembles, and you can see again, the patterns are very similar. The amplitudes are a little bit bigger in the large ensembles, because this is the ultimate drifted state, but the patterns pretty much set up early, and they are fairly consistent within each model and within each initialization method. Another way of looking at this is say how much or what % of the drift occurs by year 5. So the dark red colors here, we're taking the ratio between, for example, years 3 and year 5 drifts. So the dark red colors means that by year 3, you've already drifted by at least 80% of what the drift is in year 5. Looking at year 1, there's not many dark red colors, so of course you haven't drifted very far. And in year 1, of course, you're partway there, and by the time you get to year 3, most of the areas of the oceans have drifted at least 80% of where they're going to end up in year 5. So another way of looking at the differences between the initial states is you can look at, as a function of lead year, the agreement in sign or disagreement in sign between the brute force and the FOSSI methods. And so the idea here is the more areas that are blue, the more agreement you have in the sign of the drifts between the 2 initialization methods. And you can see the models are different. In E3SM V1, by the time you get to year 3, there's virtually no difference in the drifts between the 2 initialization methods. But even in CSM1, even by year 3 and by year 5, there's still some evidence that the brute force method was introducing a little bit different drifts compared to what the FOSSI was doing, so that there is a model dependence to these drifts and the effects from the different initialization schemes as well. So let's get back to our small number of start years, our initial years, and this is, we're going to look at a verification metric of anomaly pattern correlation between the model state. This is lead years 3 to 5, so the average of the prediction years 3 to 5. For the Pacific Basin compared to the observed anomalies over the Pacific Basin over that time period. The top one is using the drifted hindcast climatology for this small number of start years represented by these circles here. And you see it's very noisy, and really there's not a whole lot of skill across this time period. This is what you expect because you've only got these few numbers of start years and for your drifted climatology to form, so you're going to get a much noisier kind of picture. This is why you want to run a lot more samples for your model climatology to form these differences. But if you use the large ensemble now, you can see it's much less noisy. You're getting higher values here, but you've introduced a trend into this. You're getting lower values in the beginning of the period, higher values at the end. And this is what we have shown and anticipated this before as kind of one of the issues with using the whole time period for the hindcast climatology. Now this is using the previous 15 years of the hindcast climatology. Again, because we got just a small number of start years, this is very noisy, but you can see there's a lot less noise. You get higher, more consistent values when you're using the previous 15 years, using the historical large ensemble as the climatology. Now, the caveat here is that there's a well-known effect of these large volcanic eruptions where you get drops in skill after the big volcanic eruptions, like after Pinatubo, the Tervurver-Nabro period. And interestingly enough, you can see a little bit of evidence of drop in skill here at the end that is likely due to the Australian wildfire smoke, which I'm going to talk about a bit more in a minute. So now let's put this in context. So now we can compare this limited number of start years and calculating the skill metric to the full DPLE with the full number of start years every year and the 40-member ensembles. And that's the red lines here. And these are the dots from the previous plots. And you can see these are all very noisy. There's not a whole lot of agreement with the DPLE. And this is using the drifted hindcast climatology. These are all using the 15 years prior to the initial year. But if you use the large ensemble as the climatology, now you're getting better agreement with the DPLE. It's less noisy. And this seems to be an indication that you may be able to use this, the large ensemble climatology to calculate your anomalies, to evaluate skill, at least by this measure. Looking at lead years 3 to 7, you get a very similar picture, but we don't have, of course, this is beyond our time horizon of our 3 to 5 years. So finally, we can look at another way of that's often used to portray skill in these hindcast data sets. And this is taking the time series of correlations at each grid point across the whole your hindcast data set. So this again is using the DPLE to give us the best estimate of what the effects are of using the drifted hindcast as the reference climatology versus the historical large ensemble. This is now using the 15 years prior to the initial year to compute the anomalies. This is for lead years 3 to 5 and lead years 3 to 7. And you compare these panels, and there's not a whole lot of difference between them. And this is another bit of evidence that using the historical large ensemble reference climatology, at least using this 15-year prior method, you get pretty much similar results to using the drifted hindcast reference climatology. And we can use now, compare this to the all years. This is using all of the full set of 64 start years for your drifted climatologies for years 3 to 5 and 3 to 7. There's not much difference for the reference climatology using the DPLE, using all the drifted hindcasts. There is a little bit of a drop off in skill when you're using the historical, large ensembles compared to using the 15-year prior climatology. So I think our conclusion is if you're going to do this method, it's best to use the 15-year prior to the initial year to compute the anomalies, and you can then use the large ensemble as your reference climatology and get results fairly similar to what you'd have if you had the full set of start years from the decadal prediction large ensemble. So to summarize, we're looking at IPO predictions in the Pacific here, and I think we've shown some evidence that it's possible you could run a small number of start years for hindcasts and use the uninitialized free-running historical simulations from the large ensemble to form the model climatologies to compute the anomalies, to get rid of the drifts. And we can do this after about lead year 3. It doesn't work as well when the model in the early lead years when it's still drifting large amounts, but by lead year 3, it's probably okay. There's model dependence, as always, in these things regarding the relative agreement of the pattern of the drift errors between the two initialization schemes initially. But by the time you get out past lead year 2, within each model system, the drifts are fairly similar. And in that same vein, over 80% of the amplitude and pattern of the drift occurs by lead year 3 in most areas. In areas of the tropics where there's high interannual variability, there's some cases, especially in the CESM, where the drifts are still converging to their final state even after lead year 3. In the DPLE, using that as an example, the highest and most consistent skill for the IPO metric we used was using the previous 15 years to calculate anomalies for the historical large ensemble to assess prediction skill for lead years 3 to 5 to 3 to 7. And the caveat for all these things that go on in the Pacific, which has been fairly well documented now by at least 2 papers, Zhan Wu's most recent one, she's talking next. There's a loss of skill for IPO predictions after these major volcanic eruptions. And interestingly enough, if you saw my talk yesterday, I was presenting evidence that this massive Australian wildfire smoke event, 2019 and 2020, could have contributed to externally forcing this current quasi-negative IPO phase we're in, or at least the multi-year La Nina that we're in. And of course, that wildfire smoke is not in the DPLE, and therefore we would see a loss of skill without that smoke in the DPLE verifications. So thank you.
Questions for Jerry? I had one, Jerry. So you used the large ensemble for the E3SMV1 hindcasts to compute anomalies, but what large ensemble did you use? I wasn't aware that there was a E3SMV1 large ensemble.
It's not a massive, it's like 20 members. So we're calling it, it's larger than the usual 10. So it's 20, I think, is what we used.
All right, I'm not seeing questions online. Thanks, Jerry. We'll move on to Sean Wu.
Can you see my screen?
Yes.
Thanks. I'll be talking about predictability of tropical Pacific decadal variability and associated oceanic mechanisms. This is a work in progress, and I'd welcome any feedback or comments you may have. Tropical Pacific decadal variability, TPDV, is usually defined as the leading EOF mode of 10-year low-pass filtered and detrended SST variability in the tropical Pacific. It exhibits an El Niño-like SST mode in the tropical Pacific, and it also has connections with global SST variability, especially in the North and South Pacific. The time series of the principal component, leading principal component, PC1, shows that the tropical Pacific is going between warm and cold phases on decadal timescales. TPDV has substantial global climate impacts, including the decadal modulation of global mean surface temperature, interactions with interannual variability, for example, ENSO, and influences on global hydroclimate and marine ecosystems. Therefore, predictability of TPDV would have important implications for decadal predictability of these climate impacts. However, decadal prediction scale remains very low in the tropical Pacific. Here I'm showing you the correlation scale for near surface temperature in the CMIP6 initialized decadal forecasts averaged at forecast year 229. This is for the non-detrended temperatures, so the total correlation scale is high almost everywhere because the model is able to capture the anthropogenic climate change, especially the warming trend coming from greenhouse gas increase. The right panel shows the residual correlation scale after removing the forced climate change from both observations and decadal forecasts. And we can see the residual correlation scale for the internal decadal variability decreases everywhere, and there is not much scale left for the Pacific sector. It remains unclear why the decadal prediction scale is low in the tropical Pacific and what oceanic mechanisms affect the decadal predictability in the tropical Pacific. We've been exploring these questions using the CESM1 decadal prediction systems. The first is the DPLE, which was introduced in Jerry's talk. And we also make use of a parallel set of DPLE that excludes historical volcanic forcing. We have a paper in minor revision showing that volcanic forcing degrades the decadal prediction scale in the tropical Pacific. We also compare the initialized decadal forecasts with the uninitialized historical simulations, CESM1 large ensemble, to isolate the influence of ocean initialization on decadal forecasts. First, I just want to show how the observed TPDV is reproduced by the forced ocean simulation, FOSSI, which is the oceanic and sea ice conditions used to initialize the decadal forecasts. In observations, we can see in a positive phase of TPDV, we have a relaxed thermocline tilt in the equatorial Pacific. This forced ocean simulation FASI very well reproduces the observed features of TPDV, including its connections with global SST and also the temperature structure in the equatorial Pacific, as well as the time series of the PC1. How is TPDV predicted by the initialized decadal forecasts and uninitialized simulations? Here I'm showing the same analysis based on FASI and DPLE NOVOC, and large ensemble. For DPLE, we are taking the average across forecast year 1 to 10 for each initialization. And both DPLE and DPLE NOVOC can reproduce the pattern of global SST as well as ocean structure associated with TPDV to some extent. But we also identified there are biases in the Western Pacific in both SST fields and subsurface ocean temperatures, which is likely a result coming from mean state bias in CESM1. The correlation between the predicted PC1 and observed PC1 reaches 0.65 in DPLE NOVOC, which is much higher than that in DPLE. As also mentioned by Jerry, we have shown that volcanic forcing will degrade the prediction scale of TPDV because the model tends to produce decadal cooling in the tropical Pacific in response to the large volcanic eruptions, for example, El Chichen and the Pinatubo in 1980 and 90s. And while in observations, these two large volcanic eruptions coincided with the tropical Pacific warming, which is instead well predicted by DPLE NOVOC and is likely related to the internal climate variability. The rest of the talk will be focusing on understanding what oceanic processes contributing to the high predictability and scale of TPDV in DPLE NOVOC. The bottom row shows the results from uninitialized large ensemble. The ensemble mean signal of large ensemble cannot reproduce the observed TPDV, confirming the importance of ocean initialization in predicting TPDV. To identify the oceanic precursors for TPDV in DPLE NOVOC, here I'm showing the correlation analysis based on the predicted equatorial Pacific SST index averaged across forecast year 1 to 10 for each initialization year during 1955 to 2016. The first row shows the correlation of global SST and ocean temperature at the same time in forecast year 1 to 10 with this equatorial Pacific index. And then we correlate this predicted index with the initial conditions in November 0 to identify what are the important precursors. First, we don't see any significant correlations for SST over the Pacific Ocean, despite a very small region in the Southeast tropical Pacific. However, we find that the TPDV SST warming tends to be preceded by a subsurface ocean warming in the Western Central Pacific. And these subsurface ocean warming anomalies are likely to propagate into the Eastern Pacific and flip the sign of SST from negative to positive during the 10-year forecasts. Then I further correlate the predicted index with the isopycnal depth at which the potential density is equal to 25.5 kilogram per cubic meters. And we find that there are high correlations with isopycnal depth, which can well capture the temperature variability at 200 meters here. It is not only shown high correlations in the equatorial Western Pacific, but also in the off-equatorial Pacific. This indicates the role of Rossby wave reflection, which is one of the leading mechanisms proposed for the TPDV. Next, we further decompose the initial conditions into high-pass filtered and low-pass filtered variability before calculating the correlations. And we find that the TPDV predictability is mostly arising from the low-frequency variability in the initial condition. In the global SST maps, we also identify significant correlations in other ocean basins, including negative correlations over North Atlantic and positive correlations over the oceans in the southern hemisphere. So we wonder if such correlations indicate causality. So we conduct regional initialization experiments. I'm showing a case study here for 1999 to 2018. During this 10-year period, in observation, tropical Pacific shows decadal cooling, which is well predicted by DPLE NOVOC forecasts initialized in the November of 1998. The right two panels shows the initial SST conditions in both observation and fuzzy. To test which ocean basin initialization is more important to generate this decadal cooling in 10-year forecasts, we conducted a set of regional initialization experiments. First, we initialized the model with fuzzy climatology as the control run. So in this experiment, we are not giving any information about the observed conditions to the model. Second, in the tropical Pacific initialization experiments, we initialized the model with climatology everywhere, but add the full depth ocean temperature and salinity anomalies only in the tropical Pacific. Similarly, we conducted North Atlantic initialization and Southern Hemisphere ocean initialization experiments. We conducted 10-member forecasts for each experiment, and these forecasts are conducted under the external forcing during 1998 to 2018. To get the forecast anomalies, we remove the first control climatological initialization control run from other three sets, and also the original DPLE NOVOC with global ocean initialization. Here are the results from the different experiments. And we find that tropical Pacific initialization is key to generating the equatorial Pacific decadal cooling. The North Atlantic initialization is key to get the North Atlantic decadal warming here, but it doesn't generate any significant SST anomalies in the tropical Pacific. And in contrast, the Southern Hemisphere ocean initialization generates tropical Pacific warming, but it should be noted that there is an errors in the Southern Ocean warming here in predictions, which is in an opposite sign to the observations. In summary, we find that the predictability of TPDV SST anomalies arises from low-frequency subsurface ocean temperature anomalies, particularly the isopycnal depth anomalies in the Western tropical Pacific and associated Rossby wave reflection. We also explored other oceanic mechanisms for TPDV, but we haven't shown it here, including the subtropical tropical cell and spiciness advections. The regional initialization experiments suggest that the initialization of the tropical Pacific Ocean plays a key role in TPDV predictability. And I stop here and take any questions.
Questions for Jean? Dylan?
Yeah, thank you, Sean. Great talk. I have a question, I guess it's for you and also kind of Steve. I was interested by your regional initializations there at the end. I'm wondering if there's a role for the same sort of protocol that y'all are putting together with the Trans-Basin Interactions group, but for decadal timescales. I know y'all are just spinning up now, but is that somewhere you expect to go next?
Yeah, I'll mention that when we do the co-chairs update. We do have some compute allocation dedicated to that idea, decadal pacemakers, but no kind of clear experiment designed yet. So stay tuned.
Cool.
Anyone online? All right, thanks. We'll move to Christian Stroman next.
Yeah, thanks. Let's try to do this. Sorry, it's I have to give Chrome permissions to look at stuff. Sorry, my thing might disappear for a second because Google Chrome might have to restart. Sorry, this is a new laptop. Just bear with me. I'm sorry, what a waste of time. Sorry. Sorry about that. Okay, can you now see? Can you now see my slides?
Yes, you can.
Sorry, Steve. New laptop, you know, woes me. Anyway, let's get straight into action then. So I'm going to talk about some work done with colleagues whose names are listed here, including Isla Simpson in particular in the audience. And I'm going to talk about decadal predictability of a North Atlantic jet and why we think this is driven by the subpolar North Atlantic. So hopefully there's going to be a preprint available on Weather and Climate Dynamics any day now. Okay, so what's the context for this? I guess most of you are familiar with this past work by three kind of papers in particular. There's by Isla, and then Doug Smith, and also Panos Athanasiadis. And together, these three papers strongly suggest that decadal variations in the winter NAO are predictable, at least over this period, 1954 to 2015. And both Isla and Panos kind of suggest that, you know, to varying degrees of strength, they suggest that the AMV might be the possible source of this skill. But nevertheless, we're kind of left from these papers with some outstanding questions. Firstly, you know, is it really the AMV which is doing this? Can we really can we gain some more confidence in that idea? Secondly, what are the pathways and mechanisms involved? And thirdly, what exactly is being predicted here? And to explain what I mean by that, that's what this kind of schematic picture is about. So this schematic is sort of telling you that you can think about the NAO as representing two very different modes of variability. One of them coming from the latitude of the jet, and the other from the speed of the jet. These are very different, they're orthogonal modes of variability, and they have very different variability on both seasonal and decadal timescales. And crucially, studies have shown that they respond differently to thermal forcing. So if you try to do analysis with a single index, like the NAO index or something like that, you're that index is necessarily going to mix these things up, and you might have a hard time understanding what's going on. So a kind of key idea in this work we did was to decompose into these two modes of variability and see if we could get a better sense of what's going on. So if you're not familiar with the latitude and speed of a jet, like how you compute these things, the gist of it is if you have a zonal wind anomaly at 850 on a given day, then you just kind of declare that the location where the zonal wind's peak is where the jet is. And if you've decided where the jet is, then you can easily compute the latitude and then also the magnitude of that peak, of those peak winds, and that magnitude is just defined to be the speed of the jet on that given day. I mean, you just do this every single day and get your time series. Okay, so I'm going to show you some results. I'm going to use 3 data sets. I'm going to use the DPLE ensemble, which has already been mentioned several times, of course, using the CESM model. And then crucially, I'm going to make use of this seasonal hindcast ensemble based on the IFS model, which covers 1900 to 2010. So that's really nice. It covers the full 20th century. And crucially, it uses prescribed SSTs. So this is not coupled. This is prescribed SST seasonal hindcasts. And then for our truth, we're going to use Aero 20C just because it covers the 20th century. And I'm always just going to focus on kind of 10 or 30-year running averages in terms of lead times. Okay, so just a quick point about this seasonal hindcast. Of course, taking decadal averages of a seasonal forecast is not the same as a genuine decadal forecast. So it's crucial that these earlier studies have established actual decadal forecast skill. But what these seasonal hindcasts are going to be helpful for are understanding the mechanisms. And you can kind of think of it as being like a nudged decadal forecast. Nudged in the sense that every November 1st, you are bringing the forecast back to the observed atmospheric state. And in addition, of course, here we're giving it perfect SSTs. So it's a helpful tool. What does this helpful tool tell us? Well, so the top panel is showing 10-year averages of the NAO. So Aero 20C is in black, and the IFS ensemble mean is in blue. And what you can see is that you get a sort of correlation of about 0.45. So this hindcast can skillfully reproduce the variability over the entire period. This correlation of 0.45, by the way, is basically exactly the same correlation that Doug Smith and Panos find using actual decadal forecasts in the second half of the century. So that kind of suggests we get the variability all the way back to 1900 to the same extent. So that's nice. But then what the two bottom panels are showing is that in the middle, it's the jet latitude, and there you have basically zero correlation. And in the bottom panel, it's the jet speed, and there you have a correlation of 0.44 again. So what this is telling you is that all of the predictability of the NAO on decadal timescales is coming from predictions of the speed of the jet, and in fact, the jet latitude appears to be unpredictable at least in the IFS. Is it the same true for the decadal prediction large ensemble? Yeah, it turns out yes. So the top panel showing the DPLE jet latitude predictions, 10-year predictions, and you see there's nothing going on there really. It can't predict the latitude at all, but it can predict the jet speed very well. And I want to emphasize here, right, that if you compare this to the previous one where we had the seasonal hindcast, in those forecasts, we had given it the perfect SSTs and we'd given it the correct November 1st state every single year. But nevertheless, even giving it all that extra information, it doesn't actually have more skill than the DPLE. It's got completely comparable levels of skill. And we took this to be strong evidence that the signals in the DPLE and the seasonal hindcast are the same signals. And consequently, these signals have to be present in their entirety already in a single winter season. Okay, so what is driving the jet speed? Well, what you can just simply do now is we've got 3 data sets, we've got 2 forecast models and a reanalysis, and we can just look for any and all possible SST signals which are common to all these data sets, statistically significant and visible both on seasonal and decadal timescales. So here we're using very much this idea that the signals are supposed to be there on seasonal timescales already. And if you do this, then it just turns out that the only thing which pops out is what you see on this figure. It's the subpolar North Atlantic. So what this picture is telling you is that if the scale is indeed coming from SSTs, then basically it could only be the subpolar North Atlantic. And if you then compute some time series of the subpolar North Atlantic SSTs, that's the purple line, although, well, I flipped the sign there. It's negatively correlated, really, but I've just, for visual clarity, flipped the sign. And you can see that plotted together with, in black, the jet speed of reanalysis, and you get this amazing correlation of 0.97, which is high, even though, I mean, it is 30-year means, but it's still very high. And similarly, you get very high correlations in the forecast models as well. What's the pathway here? Well, we argue that it seems to be essentially tropospheric, or at least you can kind of explain it just in a tropospheric pathway sense. How is that? Well, there are 2 key points. Firstly, if you look at the kind of regression, if you regress the SST anomalies with air temperature in the vertical, that's what the plot on the left is showing in DJF, then this heating from SSTs it doesn't stay confined to the surface. It goes up quite high, all the way up to about 300 hectopascals. And so that's the filled contour in red, the heating anomaly. And then the line contour is the climatological jet in the background. This is for ERA 20C, by the way. And what you can just see is that this heating, which goes aloft, is sort of beautifully situated in front of the jet core to change the meridional temperature gradient. And if you just make a crude estimate of, well, if we assume geostrophic balance and that the only thing which is changing is this meridional temperature gradient due to the subpolar North Atlantic SSTs, then it turns out you can actually reproduce all the decadal variability in the jet speed that you see in these data sets. So that's what this figure on the right is showing. So the black, it's the actual jet speed, and in the blue, it's the this kind of geostrophic estimate. Okay, so the obvious question and controversy around all these questions is causality. Is it really the ocean forcing the atmosphere and not the other way around? And here's where this this seasonal hindcast that we use is really kind of coming into play, because these are prescribed SST hindcasts. So if you find correlations between SSTs and the atmosphere in such a hindcast, it can't possibly be because the atmosphere is forcing the SSTs, because there is no coupling here. So at least in that hindcast, the correlations are indicating causation into the atmosphere. And then pragmatically speaking, that would suggest that you should have causality in the other data sets as well, because they all have the same signals. Secondly, if you look at the heat fluxes and the SSTs in this region, they're positively correlated. So that's clearly indicative of forcing from the SSTs. And thirdly, this is a point which Isla made brilliantly in her paper. If this is really all, if SPNA is really all driven by the atmosphere, then where the heck is the skill coming from? As I showed you earlier, the only real place it could be coming from is the SPNA. And as Isla showed, the kind of stochastic forcing, short-term forcing is unpredictable. So there kind of has to be, there sort of essentially has to be something coming from SSTs. Yeah. And I'll skip over the last point because I'm already at 12 minutes here. But anyway, the conclusion seemed to be that the SPNA seems to force the jet. And I'm just going to then end with this kind of what does this result sort of suggest, morally speaking? Well, we think it suggests the following kind of picture, that on decadal timescales, the eddies are just kind of varying around their mean latitude in an unpredictable way. And that's essentially because latitudinal variations are probably a result of very complicated interactions between multiple teleconnections that therefore aren't predictable. But on the other hand, the intensity of eddies is varying in a slow and predictable way in response to the subpolar North Atlantic SSTs. And that's why you get decadal predictability of the jet speed in particular. And a key point here is obviously that, as Stephen has shown, that the subpolar North Atlantic is predictable. So I will stop there. Thank you very much.
Question from Rob.
Yeah, very interesting talk. Thanks. So I'm a bit confused in comparing this with the literature I've read previously on the DPLE about, for example, the signal to noise paradox. Maybe this is see preprint for more, but maybe you could expand on it here. I thought this signal in particular for the NAO was too weak in terms of the atmospheric response to the SSTs. So are you arguing that focusing on the jet speed gets around this problem, or could you just talk about the implications for signal to noise paradox?
No, it doesn't get around it. I mean, there's kind of no getting around it, so to speak. I mean, it's just there. And a kind of thing I glossed over in all my plots is that I'm always normalizing the standard deviation in all the time series to make everything comparable. Of course, in reality, the forecast standard deviation is always tiny in comparison to the reanalysis one. So it's not that you magically get higher standard deviations in this way. It's just that you can see the correlations. It's the correlations which become much clearer because, well, what we're arguing is that we're kind of isolating the correct mode of variability essentially.
Oh.
But yeah, it's not eliminated.
Okay, thanks. That helps. So everything was scaled up, and you're still just looking at correlations and not the.
Yeah.
Okay, got it.
Just to follow up, was the signal or the magnitude of the jet speed changes in the AFS larger than in DPLE?
Yes, I'm pretty I'm pretty sure about that, and it's just because they they only last a season, so there's not kind of they don't have nearly as much drift and things like that, so you kind of the signal isn't lost to the same extent.
Question from Hu Kim. Nice talk. Have you taken a look at skill in lens? There's a weakly positive externally forced NAO trend in lens. This is CESM lens, which may contribute to the skill in DPLE.
Yeah. So I mean, this is something we ended up not deciding not to discuss in this preprint, which is things about trends and drift and stuff like that, because it ended up getting a bit complicated and didn't know what to make of it. I do think there are unanswered and kind of subtle questions about the role of both trends and drift in generating the skill. So all we're really suggesting is that the SSTs seem to force the atmosphere, but where exactly the SST skill is coming from and stuff like that is not addressed.
Question from Matt Newman. Adam Scaife has recently argued that there is multi-year polar propagating predictability of the extratropical angular momentum due to eddy mean flow interaction triggered by SST forcing. That might be worth comparing to.
Yes, so I'm familiar with that paper. I haven't really thought much about that in the context. I wasn't sure that I didn't know that was sort of doing stuff on decadal timescales. I guess my guess was that was more relevant for shorter timescales, but maybe I'm wrong about that. Yeah, thanks for the suggestion.
Very good, thanks, Christian. We'll move on to Glenn Liu.
All right, I'm going to share my screen. Oops. All right, can everyone see the presentation and hear me?
Yes.
All right, great, thanks. Thanks for the opportunity to speak today. I'm Glenn. I'm a grad student at the MIT Hui Joint Program. Today I'm going to present work on trying to gain physical insights from the prediction of Atlantic multi-decadal variability using explainable deep neural networks. And I want to acknowledge my collaborators, Peidong Wang and Young-Ok Kwon. So to start off, looking at Atlantic multi-decadal variability, or AMV, essentially, for those who don't know what it is, it's essentially the quasi-periodic oscillation of sea surface temperatures averaged over the North Atlantic. When you regress it back to the anomalies, you'll see a characteristic horseshoe pattern with maximum warming in the subpolar gyre. And this has a periodicity of about 60 to 70 years, and it has a lot of impacts across the Earth system, from Atlantic hurricane activity, extreme temperature and precipitation over the surrounding continents, and even regime shifts in local ecosystems. And one of the interesting questions about this phenomenon is that there's still kind of the ongoing debate as to whether ocean or atmospheric dynamics are important for generating AMV. And one of the goals of this project is to try to explore if we can use machine learning to try to get at that question. And this is also very preliminary work, so I'd be really interested in your feedback on this work. And a quick note on definition. So in the most proper sense, the AMV, in order to calculate the index, that involves detrending or removing the external trend from the data, as well as applying some sort of low-pass filter. But for this presentation, we'll be focusing on trying to predict the undetrended and unsmoothed AMV index. Some of the rationale behind this is that there's been a lot of interesting literature recently on the importance of the external trend for the AMV. And additionally, we have some kind of interesting results that we want to understand in the context of having an external trend present. So the question again we're trying to ask is, if we use oceanic versus atmospheric predictors to predict the AMV state, can we gain any insight on whether the ocean or the atmosphere is more important for predicting AMV? And some of the reasons why we're taking this approach is that there's a lot of challenges associated with using dynamical forecast systems, like sensitivity to initial conditions or high computational costs. But recently there's been promise that neural networks have shown at interannual climate prediction. So an earlier talk this morning referenced the Hem et al. Paper on ENSO prediction. And the kind of question here is, does that skill really extend to longer multi-decadal timescales? And one of the challenges of understanding AMV is that there isn't a lot of data and observations. If you really trust data going back before World War II, maybe you have 150 years. So in this study, we're really going to try to focus on understanding AMV in the Community Earth System 1 large ensemble, just the first 40 members. This gives us about 3,440 years to play with. And finally, kind of one of the main, I guess, setbacks of using machine learning is that it's often seen as a black box where it's really hard to understand where is this predictability coming from. But as was excellently described by Maribeth yesterday during the seminar, there's a lot of different ways that you can use to basically understand what has a neural network learned. Like given a sample, you can recover a heat map or relevance map to understand which regions were important for prediction. So we're going to use one such approach, layer-wise relevance propagation, in this study. So what are we trying to do here? So we have a neural network and we give it some sort of predictor. It can be sea surface temperature anomalies, which are used to calculate the AMV index, some sort of oceanic variable like sea surface height or sea surface salinity, or some sort of atmospheric variable like sea level pressure. We then ask the network 0, 3, all the way up to 24 years later, what is the AMV state going to be? Is it going to be positive, neutral, or negative? And we kind of determine these using a 1 standard deviation threshold. In terms of the architecture of the neural network, we've tried a few architectures, but for these results we'll be sharing, we used the convolutional neural network that was used in Hem et al. 2019. That was pretty successful at ENSO prediction. And we also used a simple 4-layer neural network with 4 layers and 128 neurons each. So for each, essentially we train a network to predict AMV at a given lead time, given a specific predictor. And we train 50 networks to account for variation due to the initialization of the network weights. This leads to a total of 1,800 networks, which we have trained for this project. So first, we're going to try to compare, is there a difference between using convolutional neural networks versus fully connected neural networks? And the results I'm going to show here are using SST as a predictor. And the results are pretty much the same for the other predictors as well. As a baseline, we use a persistence baseline. So essentially, at lead time 0, whatever AMV state it is currently will be the same state n lead times later. So what I'm showing here is the skill from 0 to 24 years and the accuracy on the y-axis. we see here that both the CNN and FNN outperform the persistence baselines and exhibit comparable accuracy. So you can see the yellow and the blue lines are pretty much comparable, and they fall well within the sort of 95 confidence or 95% of the 50 different initialized networks that we've trained. And why might this be the case? Well, you can think of the idea of how CNNs are really specialized for something called translation invariance. So as an example, in image recognition, CNNs have to learn how to identify features that no matter where they appear in the image. So in this example, you can see that this interpretability method reveals that in order to identify a barbell, you have to find it no matter where it's located in the picture. However, perhaps for the case of large-scale prediction, we're thinking that small-scale features are not as important for predicting the A and B state, though we're still thinking of different ways to investigate this hypothesis and welcome any suggestions. So because they perform so similarly from this point on, we're going to focus on the results for the simpler fully connected neural network. So what are the differences in skill by predictor? So let's start by focusing on the positive A and B state. So we use sea surface temperature as a predictor. You see that initially performs pretty well, but after about 6 years, the skill plateaus at about 50%, and it outperforms the persistence baseline. When we compare it to an atmospheric predictor, we see that generally the atmospheric predictor does worse compared to SST. But when we look at oceanic predictors, so here you see the sea surface height in blue and sea surface salinity in pink. It seems to outperform both sea surface temperature and sea level pressure for predicting positive A and B states. You also notice that the spread in the models, which is the shading, is slightly narrower for these oceanic predictors, suggesting that the skill for these predictors are much more consistent compared to the other two variables. So this is the case for a positive A and B state. What about a negative A and B state? So here I show the same plot, but for the negative A and B. And the main difference here is that the differences in scale between sea surface temperature and the oceanic predictors are a little bit smaller. But overall, it seems like the mean of the oceanic predictors is slightly higher than using sea surface temperature as a predictor. Finally, for neutral states, we see that all the different predictors struggle, and overall the performance is much worse compared to the persistence baseline. So now that we've looked at some of the differences in skill by predictor, what are these sources of predictability? So we're using this layer-wise relevance propagation method. So essentially, for a given prediction, like a positive A and B, you can backpropagate the weights of the relevance through the networks and recover which regions of the input are most important for that prediction, and use a series of propagation rules which are outlined in this excellent review paper by Montavan et al. In 2019. For this particular result, I'll be focusing on correct A and B positive predictions and looking at the composites of relevance for the top 25 networks. Here I'm showing the relevance map for sea surface temperature for a lead zero prediction. Again, darker red indicates that these regions are of higher relevance or more important for making that prediction. If this looks familiar, there's no coincidence. It kind of resembles the canonical A and B horseshoe pattern, where the maximum is in the subpolar gyre, as well as in the tropics, and there's a lower, less important region within the subtropics. But what about longer lead time? So as we go back in time, you'll see that the region of maximum relevance contracts to an area south around the Grand Banks along the Gulf Stream and North Atlantic Current. So this suggests that the focus or important region of predictability contracts to this more focused region at longer timescales. But if you remember from the previous slides, sea surface temperature wasn't as good as an oceanic predictor at longer lead times. So how do these relevance maps look like for sea surface height, for example? So this is what I'm showing on the bottom row right now, and you'll see that one consistent feature that pops out throughout all these different lead times is that this sort of Gulf Stream, North Atlantic Current region seems to be pretty important for predicting on these much longer timescales. So very quickly, some kind of takeaways for this. We see that complex architectures like using a CNN does not necessarily lead to more accurate A and B prediction. We also see that oceanic predictors offer more predictive skill, or at least more consistently higher predictive skill on longer timescales, lead times, and also that the Gulf Stream and North Atlantic Current emerge as important regions for long-term predictability. Of course, there's a lot of work to do from this point on, and I'm really interested in what you have to say and some feedbacks and suggestions, but kind of the first step would be investigating the dynamics or causality behind why these regions might contribute to higher skill and prediction at these timescales. Also exploring how the presence of an external trend contributes to the predictability. So much of the differences between these predictors when the external trend is removed is lost after 6 years. And finally, some other steps are to examine how these relevance maps are sensitive to other explainability methods, and if this is applicable in terms of transfer learning to observations, reanalyses, and other models. So that's about all I have for today. Thank you for listening and looking forward to your feedback. You can also reach out to me via email over there. So thank you.
Well, there's also a question online if you want to take that first, but I guess I'm talking already. So nice, thanks for the clear talk. And I saw that you mentioned this in your future directions, and I think it's an important thing to look into more. But yeah, curious about this not choosing to remove the external trend. I think that, I mean, if you're predicting something 20 years out, that is likely you've predicted the trend. And I mean, from the layer-wise relevance propagation, you do seem to be capturing on features that are getting the internal variability, but somehow there seems to be some combination of the forcing and internal variability in your results. And I'm interested if you've done any more to look into that yet, or what you have planned.
Yeah, so I've done a little bit of investigation, but still need to do a lot of work along that direction. For example, I've done, I can share my screen again, but a simple linear regression of the ensemble mean or the external trend AMV index on these variables. And the same regions pop up, the same regions do pop up. So you can see over here, I essentially just regress the ensemble mean AMV index to each of the different predictors. And you can see, for example, for sea surface height and sea surface salinity, this sort of Gulf Stream / North Atlantic current region pops up as some of the largest signals. But there are also other regions that have large signals but don't quite show up on the relevance map. So in terms of dynamical understanding, I still need to think about different ways to investigate this, but we have also looked at the distribution of predictions. So is the model, for example, simply just predicting more positive AMV states towards the end of the period? And actually, it doesn't appear to be that way. In terms of the distributions of the predictions, the neural networks are managed to learn that sort of multi-decadal oscillation where they make more negative predictions towards the middle and more positive predictions towards the beginning and the end of the period. So it seems like there might be something more going on here than sort of a simple, I guess, the effect of the linear trend, but kind of clarifying that would require a bit more investigation. I'd be curious to hear if you have any suggestions.
Online, Jacob Schlur is saying, nice talk. Why do you train different networks for different lag times and different variables? Would you not expect to get the best model by stacking the variables in the channels of the CNN and predicting all lag times? This way you could also use the relevant propagation to identify which variables are the most important.
Yeah, thank you for the suggestion. So I think part of it is part of it was a practical consideration. So by stacking all the different variables and all the different lag times, the input size of the neural network is much larger, so it takes much longer to train. So by sort of separating this task into different lead times and different variables, I guess our goal is to try to see if we can get some sort of physical understanding, maybe by seeing if certain predictors lead to more predictability and kind of train more networks to make that that are more specified at a specific task. But that is a possibility, though I also imagine if you have a single model that you're training to make predictions across multiple lead times, just thinking of it, I guess, in an optimization sense, there might be, you might have some, I guess, some losses at different lead times as it tries to be optimal for all these different lead times, which maybe different processes contribute to, if that sort of makes sense.
Can I follow up this, or do we run out of time?
Go for it.
Yeah, just a quick question. So I think you could, with the like when you have the fully connected neural network, it should have, because you need to use every grid point as an input would be a feature, right? So the number of parameters would be much larger with a fully connected network than it would be if you have in CNN, which is stacked variables.
Right.
And
Yeah.
then
Mhm.
what I would do, I mean, I don't know if you saw my talk, but you should look into this film, the feature-wise layer modulation, where you kind of could inform the network which lag time to predict.
Oh.
And if you do this, then it is kind of learning different networks, but they share their weights and they are kind of scaled for the different lag times. And this might give you the same effect and would be actually way more data efficient, because this way you would not have to train all these different networks. And you should be actually get a much better performance and could look then in the relevance map at like joint variable highlights basically, and you could get like a state where you could get kind of more information from, I guess.
Yeah, I haven't tried that before, but I'd be really interested in trying that out. Thank you for the suggestion.
Sure, you can shoot me a mail if you want.
Yeah, no, definitely.
All right, thanks very much. In the interest of time, we'll move to the final talk, last but certainly not least, by Dylan and Maya.
Does it matter which one I use? They're both dead, I think.
Even if you switch this one.
Yeah. And left was off. That sounds good. Test, test. Can you hear me online? Think so.
Yes, we do.
Yes. Okay. I guess I need to pull up the talk. There we go. And as Clara mentioned yesterday, now for something entirely different. We're going to return back to seasonal forecasting world, and we're going to be looking at much smaller scales and thinking about dynamical forecasts of coastal upwelling in the California current system. This is something that NOAA is starting to dive deeper into, trying to develop more operational forecasting tools specifically for the ocean. So after this talk and when we get into the discussion, I'm excited to hear more about opportunities for integrating ocean forecasts into what we do, because we have a lot of stakeholders who are interested in the forecasting capabilities of both physical and ecological variables. So for those that are unfamiliar, the California current system is very important. There are a lot of important marine resources that need to be managed, and those management decisions take place on a variety of different timescales and a variety of different ways. And one of the most important components of the California current system that influences many of these marine resources is upwelling. And dynamical ocean forecasts can help make management decisions related to variations in things like upwelling or other variations in the California current system, which is something that we're trying to develop. So thinking about upwelling in the California current system, it can sort of be broken up into two components. This is sort of encompassed by this Coastal Upwelling Transport Index, which was developed by Jaycox et al. In 2018. It takes into account the wind-driven Ekman component of upwelling along the U.S. West Coast, which is driven by northerly winds along the coastline. But there's also an important geostrophic component in the horizontal direction that's set up by a north-south gradient in sea surface heights that drives typically an onshore geostrophic flow that can also influence vertical transport of colder waters from below, but also nutrients. And this is mostly important for Southern California, but it's an important part of the equation. The issue is that if we want to start looking at forecasts of parameters that people care about in the ocean, we typically don't have all of the data available to us to evaluate the forecast skill of these things. For example, if I wanted to evaluate the forecast skill of CUTI, this Coastal Upwelling Transport Index, I would need often daily mean wind stress, daily mean sea surface height, and daily mean mixed layer depth. And these are not often things that are saved on seasonal timescales for a large subset, at least, of seasonal forecasting systems. But we can start to address this question at least for the Ekman transport component of it, because most models have saved daily mean wind stress. And it'll become apparent here in a second why we need daily mean forecasts for seasonal forecast skill assessments, basically, at least for something like upwelling. So to assess our ability to forecast this thing, we need some measure of truth. And as you can imagine, we don't have fantastic measurements of upwelling in the historical record. So our measure of truth is actually coming from a regional data assimilated ROM simulation from 1988 to 2018. It was developed by UC Santa Cruz. And they have, because it's a simulation, they have all the data you could want, but I'm going to be specifically looking at daily mean Ekman transport and the vertical velocity associated with that Ekman transport in these 1-degree boxes, which are outlined in black here, up and down the US West Coast. And I'll be evaluating the forecast skill of this Ekman transport term in the ECMWF seasonal forecasting model, which is one of the models that is able to save daily mean reforecasts for 7 months, initialized every month from 1988 to 2017. And I'm embarrassed to come to a CSM working group meeting and not show CSM model validation, but it is something that we have and we're working on, and something I can show at a later date. But you can at least get a sense for the method with the ECMWF framework for now. So ECMWF has 25 ensemble members on a 1-degree grid, and we're basically going to be looking at upwelling in 1-degree boxes, basically the nearest grid cell to the coast. So it's important to keep in mind that these models were not tuned at all to take into account coastal processes, because it's just sub-grid scale. Even though the model is run on a 1/4 degree, typically these models are not parameterized to care about forecasts along the coast. So this is not what the model is intended for, but it is possible that it could be doing something useful, and that's kind of what we're after. And I'll just reiterate that it only saved daily mean wind stress, so we can only look at Ekman transport driven vertical velocity. We can't look at this geostrophic term. Just to simplify things, we're going to look at forecast skill broken up into 3 regions: the Northern California current system, Central California current system, and the Southern California current system, separated at Point Conception and Cape Mendocino. Okay, so let's just look at the skill evaluation very broadly. The top is the forecast skill as measured by the anomaly correlation coefficient for the Southern California current region, and the bottom is the RMS error. The stippling is telling you that the forecast skill is significantly better than damped persistence at 90% confidence. A lot of these correlations are actually better, significantly above 0, but in the ocean, on these timescales, damped persistence is often your best first guess. So we have to beat that. I will make the argument here that there is some hope that the model is doing something reasonable, even if there aren't too many stipples here. There is some physical, I think some physically consistent thing going on here, and that's this horizontal, or this diagonal orange stripe here, which is very, it's a very common feature in seasonal forecasts of the ocean in the California current system, at least, and it's basically the ENSO stripe is what it's referred to. It's telling you that you're getting a skill bump in boreal winter because of the influence of El Nino, regardless of when you initialize the model. So you can initialize it in spring, summer, fall. As long as it encompasses the winter, you get that skill bump. And this is generally true for all of the regions, although RMS error does increase as you go further north, because the wind fields associated with Ekman transport and Ekman pumping or suction are noisier at higher latitudes, so it just becomes harder to forecast. And in case you needed more convincing that ENSO is the most important driver of seasonal forecast skills, or seasonal forecast skill for a variety of variables, here's another piece of evidence for that. Up here, these plots are showing the skill above persistence in the dynamical forecast system for all years, years just for ENSO events, and neutral years. And this is just highlighting that the seasonal forecast skill that is present is being primarily driven by ENSO. Again, this is for the Southern California current system. But this is generally true, once again, for the central and north, although it does start to get a little bit noisy. And you get less of that coherent sort of ENSO stripe. So this is actually what I'm trying to forecast, and I realize I probably should have led with this, but upwelling is actually a pretty noisy time series. This is the QD index for 1 latitude, 40.5 degrees north, for 1 year, and these are the daily mean values. So you can see anything above 0 is upwelling, anything below 0 is downwelling, and it's a fairly noisy time series. But there's a lot of features here when you integrate this sort of time series over the course of a year that a lot of marine resource managers look to for signals for what the physical system is doing and how the ecological system may respond to those physical changes. And we quantify that using what's called cumulative upwelling, a cumulative upwelling index, where you basically just integrate, every year you integrate the QD index from January 1st onwards. And when you do that, you get something that looks like this blue line. And you can start to define different, what we call upwelling phenology terms to indicate where you are in the upwelling season. For example, the spring transition is the minimum of the cumulative upwelling index over the course of a year. And that is the signal that you are transitioning from a time of mostly downwelling to a time of mostly upwelling. And then you can also look towards the max, the greatest cumulative upwelling value, as giving you a sense of when you're sort of at the peak of upwelling season, and then obviously the peak is the end of the upwelling season. And so these are different things that would be useful to forecast on seasonal timescales, so that folks can get a sense of whether upwelling season will be later or earlier than normal, and then plan accordingly for when and where they want to open fishing grounds, for example. And again, when I try and do this, I have to use the Ekman transport term because I just don't have access to any daily mean sea surface height or mixed layer depth data. Okay, so we're going to look at the forecast scale of the spring transition. Just to give you a sense of what this looks like, this is the cumulative upwelling for 39 degrees north in the year 1998, and this is from observations. By observations, I mean this data assimilated ROM simulation. But this is the observed spring transition for that year. It happened sometime in mid-February and year day 51. And we can try and forecast this by integrating our forecasts based on the January initialization and integrating the forecasted Ekman transport term. And you can get 25 different guesses at when the spring transition occurred. If you average them all together, you get an ensemble mean guess of when the spring transition may happen. And in this case, at this latitude in this year, you can see that the model does really well. There's only a 3-day error in when the transition to upwelling is forecasted to happen. Obviously, that's not going to happen every year. You can do this again at the same latitude, but for a different year. And you can see that the forecast is much worse. It's off by about a month. But you can play this game for every year and get a sense for how well the model can forecast the interannual variability of the spring transition at a given latitude. And it looks like something like this. So this is busy, but just focus on the red for a second. That's the interannual time series of the spring transition and observations for 39 degrees north. The black line is the ensemble mean estimate of the spring transition in the model for a January initialization. And then the horizontal gray lines are the individual ensemble member guesses of when the spring transition is occurring. The take-home message here is that the model is doing something sensible. It's getting particularly these peaks, a lot of the peaks in sort of late spring transition times, and there's an overall significant correlation of 0.62 and a relatively low RMS error of when the spring transition is forecasted to occur. This is just for one latitude, though, so we can repeat this process for all the latitudes and see how we do, and it looks something like this. So this is showing you the anomaly correlation coefficient and the RMS error for the interannual relationship or the annual forecast of the spring transition relative to observations as a function of latitude. And for 3 different initializations, either November, December, or January, and in any of those cases, we're integrating from January 1 as far as the cumulative upwelling index goes. And the take-home message here is that the model does skillfully seem to predict the spring transition, but mostly in the central California current system. Once you get too far north, there's just too much noise. There's too much wind variability, and it's not something that's easily predictable. If you get too far south, it's upwelling all the time. And it's not something I have to show you here, but it's trivial to forecast the spring transition to upwelling season in the Southern California current system because it's always upwelling. But the Central California current system seems to be that nice sweet spot where we might have some useful skill for folks to make decisions based off of. So I'll summarize there. The ECMWF model does seem to have some prediction capabilities at getting upwelling intensity, something like 5 to 7 months out, and that seems to be primarily linked to ENSO, like most things are in seasonal timescales, particularly in the California current system. And the model does seem to have some skill at predicting the spring transition in the Central California current system when initialized in November through January. So with that, I'm happy to take any questions, and I'm looking forward to discussion afterward. Thanks. Yeah, go ahead, Isla.
It seemed like when you had your bar plots of the different years, there was quite a lot of variation in the spread across the members, like 2010, they all agree. Do you think those are real variations that you can understand?
You mean in the model spread?
In the spread, yeah.
Yeah, that's a good question. It's sort of, yeah, I guess I don't have a clean answer for you here. We haven't looked too deeply into the model spread just yet. But I agree that there's huge swings in what the model is guessing at the spring transition. But it's only when you take the ensemble mean that you end up getting some nice correlation here. But it is something to explore for sure. Can't decide if Jacob's talking to me or the previous,
No, that was
the previous one. Okay, sounds good.
So I had a question on this as well. I mean, I was expecting to see small spread in 98, and I assumed you chose that because it's the 97, 98 El Nino, and you clearly get good skill, but with large spread in that year, I guess your ENSO stripe didn't really pop out in this figure to me.
Yeah, so it also kind of depends on where you're at. This is 39 North is something like Central California current system, and a lot of the ENSO teleconnections historically have been shown to happen mostly in the Northern California current system. So if I honestly can't tell you because I can't remember what the time series looks like for 45 degrees north, for example, but it's possible that ENSO signal will be more apparent further north you go. That said, I agree, the spread is huge. There's not a high signal to noise ratio going on here. I guess both to your and Isla's point, it'll be important to understand what's driving that spread and if there's something real going on here or if we're just getting lucky. But I think one way to get to that is by also comparing across models, and we're folding in more and more models to sort of see if there's something useful amongst them. You had your hand half raised, sorry, go ahead.
Just, do you get the same result if you average upwelling across the ensemble members and then take the STI instead of finding the STI and then averaging it?
Yeah, so you could do that, but what ends up happening is that you end up getting a very smooth, an artificially smoothed answer on what the cumulative upwelling is, so that it'd be the average of all these gray lines.
Yeah.
And sort of a rule of thumb is if you're trying to forecast something, you try to get that something in all the ensemble members and then take the ensemble average. And in this case, that something is the spring transition. But it's a good question, and it's a sensitivity test that we have tested, we have done.
Nish has a question there.
Nish, have you looked at subseasonal variability within the seasonal forecast skill? Is there more skill in early season versus late season? So not directly in that manner. We have actually looked at subseasonal forecast skill of upwelling in a subseasonal forecasting system, but it has it's just a noisier thing to look at. So I don't have a very satisfying answer for you, Anish, but it is a good suggestion. Yeah, go ahead, Hayan. I think you might be muted or we can't hear you, one of the two. Maybe type the question, Hayan.
Can you hear me?
Oh, a little better. Yeah, go ahead.
Okay, so I have a very general question about the resolution requirement for simulating coastal upwelling, because this is also an ongoing DOE effort. So do you have any comments on what would be if we want to simulate coastal upwelling, do you think there is what would be the minimum resolution required?
Yeah, that's a good question, and not something I'm ultimately prepared to answer right now because I don't have a very satisfying answer for you. This model its simulation resolution is a quarter degree, and that seems to be good. You want something that's eddy permitting because you want to make sure you get the SSH gradients correctly, and there's a lot of eddy activity in the California current system. If you really want to, I would say the most important thing is being able to resolve what's going on the continental shelf, and like an impacts perspective, and the shelf along the US West Coast is only like 25 kilometers wide. It's extremely narrow. And a lot of the times we care about these really narrow upwelling features that are definitely not resolved in this model. But it seems that at 25 kilometers, we're getting something reasonable, at least in ECMWF. But if you want to get, I honestly don't know what the biases are in this model either. I realize I'm having a lot of no answers here, but this is something I put together this past summer, so it's been a while since I've thought about it. But it's a good question, Hayan. And if you come to an answer, please let me know so I can think about it more.
Thank you.
Yeah. Maybe we should.
Thanks, Dylan.
Yeah,
Maybe we'll
thanks.
transition. Okay, time for the co-chairs update. I think my fellow co-chairs are online. I know Yaga has to leave at 3, but this can be quick, and then we can get into discussion. So I just wanted to start with just an overview of sort of core assets of the working group and just remind people, particularly people maybe who haven't tuned in before, of the data sets that this working group is disseminating. We've got reforecast or hindcast sets from CESM1, subseasonal to seasonal. CSM1 also contributed seasonal hindcast to the NMME project. We've heard a lot about the DPLE, which used CESM 1.1 system with this 40-member large ensemble. More recently, we've augmented these collections with CESM2 versions. So we heard in Yaga's talk about the CSM2 S2S set CAM6. There's also a high top Wacom 6 S2S reforecast set. Both of these are documented in papers by Yaga. We have now the seasonal to multi-year large ensemble, so focusing on this kind of intermediate seasonal to interannual timescale using CESM2. It's a 20-member ensemble, initialized quarterly over quite a large historical window here. That publication came out last year. Less well advertised is the fact that we extended the November 1st initializations of SMILE out through decadal timescales, but we only did that for 10 members, so it's kind of a mini decadal prediction ensemble using CESM2, but it does span kind of this large decadal time span. I'm not aware of anyone actively analyzing that, but it's available. If you're interested, get in touch with us. And as I'll mention, we do plan to augment that ensemble size, make it more useful. And then you heard in Yaga's talk today about the S2S perturbed initialization experiments. There's a paper in prep, and so those data sets will be coming available shortly, certainly this year. And then in my talk, I talked about sort of these pacemaker experiments built on top of the SMILE control. We completed a preliminary Atlantic pacemaker experiment initialized in February. I plan to increase the ensemble size of that. And so this is another sort of asset that will be coming available this year. And then, as I mentioned, we do plan to expand the ensemble size of the CSM2 decadal prediction set to 15 from 10. So I don't think we're going to aim for a large ensemble with CSM2, at least with our current allocation, but 15 should be better than 10. All right, so we went through the exercise in the fall of submitting the CESM compute allocation proposal, and that was successful. So we got all of the core hours that we requested for this 2-year time span here. This working group got 22 million core hours in year 1 and a little bit more in year 2. So that will be, particularly in year 2, allocation that can be used on the new derecho supercomputer. And we solicited feedback from working group members back in June as to what we should put into this ESPWG proposal, and we did our best to reflect the feedback that we got. And let me just kind of walk through this briefly. We have a development allocation and a production allocation. For the development, we kind of decided to allocate just some compute just for S2D sensitivity studies, sort of very generic idea of kind of building on these control hindcast sets that we've created and exploring sensitivity, for example, to ocean initial conditions. conditions or ocean initial condition spread, which we currently lack. How much is that impacting our predictions on subseasonal to decadal timescales? Land initialization, something that we have not focused a great deal on, certainly not on the longer timescales, but we don't really have a good sense of what the sensitivities are. So this is very open-ended and very much sort of looking for people to come to us with ideas and take the lead and get free compute hours to see those ideas realized. Also in development, we allocated time for testing the new CESM3 model in initialized prediction mode, both S2S and S2D, likely in collaboration with the Ocean Model Working Group, because they're the ones who are going to ocean and sea ice initial conditions using the FOSSI methodology that has worked well in the past. We have some compute allocated for testing the benefits of initialization using DA. And then another idea is to explore online bias correction methods, so potentially machine learning bias correction methods. On the production side, there are plans to extend our existing hindcast sets to near real time, both for S2S and S2D. So in year one, we will extend the S2S hindcast set through October 2023 initialization, and then forward a year in year two. And then we'll try to do the same with the CESM2 decadal prediction set. So in this year, try to update initializations through November 2022 and then up through 2023. Caveat here is that we don't have a working group liaison, so you know, a lot of this is aspirational, but we need people to actually do this, so it kind of depends on people's availability. Another production idea is to rerun the S2S set with land all but one initialization method. I'm not sure what that means, but if Yaga's online, maybe she can chime in there. And as I said, expand the CESM2 decadal prediction ensemble size, complete more of these TBI SMILE pacemakers. You know, we only allocated for 12-month simulations, but that's probably too short. I think we want to get into year two. We want to get back to 1980. So we may be tapping into other parts of the allocation to complete these SMILE pacemakers. We've kind of done the initial cut at the Atlantic, but the Pacific and Indian pacemaker experiments can sort of leverage the technology that's been developed and get underway this year. And then, as Dylan asked earlier, another idea is to extend this to decadal timescales. So using now the new CSM2 DP as a control, we can think about decadal hindcast pacemaker experiments. What those would look like is up for discussion. They could follow the TBI protocol, or they could be something completely different. Again, it really depends on people showing some entrepreneurial spirit and saying, I've got a great idea and think it would help the working group, and we can give you the compute to do that. One idea that has already been shelved is contributing to the WCRP Spark DCPP volcanic readiness exercise. This is something that Bill Merrifield is trying to get all decadal prediction producing centers to participate in, which is rerun your real-time decadal forecast with a synthetic volcanic eruption, just to basically get the infrastructure in place in case a volcano does go off that invalidates your decadal forecast. Would you be prepared to rerun those kind of in a short time frame? We shelved that because they're using this like EasyVolc or something, I kind of forget, aerosol forcing. That is not the way that we implement aerosol forcing. too much work to contribute to that. So that frees up 500,000 core hours, 0.5 million core hours. So, the only other thing I wanted to mention was, we have put together this Python package calling it ESP Lab. The goal is community developed toolkit for efficient interactive analysis of initialized prediction ensembles. I used this for the SMILE paper. I'm finding it pretty useful in my own work, but maybe it's just me. I don't know if other people are using it, if this is a good idea, or if people have their own kind of software tools that they use. But I just wanted to advertise it again. It's on GitHub. Certainly welcome contributions and collaborative effort on analysis. And with that, I'll just open it up to discussion, questions, comments.
I have a bit of a remark to give. If you are listening to me, this is Eniola.
Yes, we can hear
from
you.
Nigeria. Yeah, so I just wonder how I can be more involved or useful in this group, right from where I am here in Nigeria. So because I can see that most of the people in the group are far in the United States. So I wonder how can I be more improved, how can I be more involved in the activities of the group?
Great question. Well, I think you've made an important step by participating today, and you can look forward to our next working group meeting in June, which will be the CESM annual meeting, and hopefully you can participate in that as well. You can kind of keep up to date on the happenings by just looking at the ESPWG website, finding the data sets that are available, the upcoming events, and certainly I think if you were to start to utilize some of the CESM prediction data sets in your work, that would help tie in your work to that of the working group. Dylan.
I guess I just want to reiterate something I mentioned in my talk, which was sort of the gap in ocean forecasting relative to atmospheric or climate forecasting. We being like at least our group at NOAA are becoming increasingly interested in producing these operational forecasting tools for the ocean. But it's often difficult because a lot of modeling centers don't save some of the requisite ocean variables. So is there an opportunity before these runs are made to inform what variables might be useful to save and help guide that decision making?
Absolutely.
Okay.
We're certainly interested in hearing if there are any glaring gaps in the data that we're saving. And if there are runs coming up that you're particularly interested in, I think you feel free to make your voice heard, to the co-chairs. Like when we put together the SMILE, we did go through a round of soliciting feedback on output. I don't recall that we had a lot of external input. Like it kind of in the end, it was kind of internal CGD decision making. But we always want to hear like if there are some key fields, some key frequencies that are missing.
Yeah, I guess I find that I often want to use CSM forecasting products, but then I run into this situation where you just happen to not save the variable that I happen to need in that moment. And that's not just a CSM problem, that's a problem in NMME doesn't save most ocean variables that aren't at the surface. And I'm not advocating for 3D ocean variables, but like simple things like mixed layer depth or sea surface height
at daily time
scales would be a huge help.
Yeah.
Especially if there's some effort to, with the Climate Ecosystem Fisheries Initiative, to develop regional ocean forecasting systems that are forced by global forecasting models. And we can't force our ocean models without having like some of these global outputs. So anyway, that's a discussion we can have like down the road, but I just wanted to make sure that door was open.
It's definitely open.
Can I ask a question to Dylan? Is this specifically for the initialized forecasts, or do you also think generally CMIP6 runs and things like that, CMIP whatever?
I have no.
Large ensembles.
Yeah, large ensembles typically have all the data I need for in the ocean. It's more of initialized forecasts because they're producing so much data, especially in real time. It's just hard to store it all, and I don't expect people to store it all. But if we're going to prioritize, I guess my point is that if you want to broaden your user base, this might be one easy way to do it. Because I think these runs are extremely useful for more than just climate problems. I think they could be used in an operational sense if we can get a sense for how accurate they are for some of these other things. And then I guess kind of on that note, if you don't mind me following up, I'm curious, what is the resolution of the S2S runs that you're developing for the ocean? Like what is the simulation resolution and what is the output resolution? Like what are you saving? Or what are you planning to?
Are you still there? And I don't know if you can comment on, I mean, the horizontal resolution is 1 degree in all of these.
Okay. I do see Yaga on there. I don't know if she wants to add anything to that.
Sorry, I was typing back to Eniola. So yeah, we just used the default 1 degree resolution.
Okay. I guess just continuing to advocate for the oceans here a little bit. If it's a priority for S2S forecasts to be useful for ocean decisions, and I will admit that like a lot of ocean decisions happen on these S2S timescales, even though the ocean is dominated by longer, low frequency things. That when you look at S2S forecasts of the ocean, your spatial scale necessarily decreases because the ocean is so sluggish. So it's really not useful to look at like global S2S forecasts of oceanic variables. You really need to zoom in on the coastline and look at high frequency, quote unquote, high frequency variability that is important on those timescales. So we can't do that if the resolution of the ocean model isn't capturing what's going on along the coastline. I'm not advocating for a 12th degree, CSM's S2S product, but it's just a general comment that if you, again, want to broaden your user base to include ocean forecasting on S2S timescales, you necessarily have to start resolving some of those coastal processes where it's actually going to be used. We just simply won't use S2S forecasts out in the middle of the North Pacific.
Yeah. Have you looked at the CESM S2S ocean output at all?
I have a little bit, yeah. I had to put it down because there weren't the variables I needed. I think wind stress was saved. I was looking at it for upwelling purposes, and wind stress was saved, sea surface height wasn't, mixed layer depth wasn't. But it was also 1 degree, which limited its use in our purposes as well.
Yeah, maybe you can send me an email because I thought we were saving mixed layer depth. It was one of the variables that I was fairly sure we were saving.
Okay. Yeah, I can go back and double check. I think I reached out to both you and Steve sometime in like August about this. There was one variable that I just that nobody has, not just you, but like nobody has it. And I can't recall exactly how that email chain went, but.
Okay, we can double check because some of the data, the ocean data may not be available online, but we might have it.
On Cheyenne or something, or Casper.
Yeah.
Gotcha.
Yeah.
Okay. Anyway, I don't mean to dominate the discussion. It's just something that is worth thinking about if you want to expand your user base for ocean-oriented forecasts, which is, I would say, about 2 decades behind atmospheric-oriented forecasts in an operational sense.
I think the next kind of critical juncture when we're going to reevaluate output is when we start doing CESM3 initialized hindcasts. And that's when we're really going to make an effort to get feedback from people like you on what should we include kind of moving forward. Because we're not going to rerun all of our existing hindcasts to save extra output. And I saw this comment from Sanjeev about missing soil moisture variable from SMILE, and I've noticed that myself, and I really don't know how we missed H2O SOI. I don't have a good answer for that. Anyone else from online? We're starting to dwindle in participation. Judith.
Not online. Could you put up the allocation for the next 2 years? I'd be interested in the plans, or there was the S2D online bias correction. You don't need to put it up, but it was number 5 on the left side. I was wondering what the plans are for this and who's the sort of contact person for this. Because we are working on online bias correction methods using nudging and machine learning, and it would be nice to link with that effort.
Jerry, I think this is sort of a catalyst placeholder here. I don't know if you're online. I think Maria Molina and maybe Katie Dagan were sort of people that were potentially interested in exploring some kind of machine learning correction. Kirsten Meyer, I think hers is more offline, but you know, to be honest, we're as co-chairs coming up with themes and then trying to match the themes to people to actually execute. And so I just want to reiterate that, you know, like Yaga and I are not going to do all this. So, you know, I really do mean it. If you have like a good idea that you think is relevant to the working group, we, you know, really solicit, you know, those proposals, and we'll give you the compute time to run them.
Yeah, just to state, there's a very big collaboration using machine learning to detect and correct coupled model biases, which would align really nice there and should be collaboration rather than repetition. Yeah.
Yeah, but it gets at, you know, the question that Antonietta asked me, which is how big are the climatological biases in the tropical Atlantic, and they're huge. And you know, I would think that if we could come up with some online SST bias correction methods, you know, if it's sophisticated or if it's just flux correction, like I think that would be an interesting thing to explore.
I was just wondering about high resolution, whether anything's come out of IHESP that motivates the working group to look at that more.
Yeah, I was hoping Gokhan would say something about his new high resolution prediction project, but he's in the CAB meeting in DC. But you know, that work is continuing. I think the preliminary set of initialized decadal hindcasts from what was formerly known as IHESP will be made available this year, and that will be like a really awesome asset for this working group. You know, I don't know that we're going to distribute it. It's probably, I think data distribution of that is problematic and hasn't been solved. You can't just download all of this high resolution data because it's too much. You kind of need to get compute where the data is, and you know, it's still very much sort of getting the data through back channels at this point. We do have a set of it here at NCAR, and I would like to see that kind of made public and advertised, maybe by the June workshop.
I'd be interested in looking at it if it's on Casper anywhere I can see.
Yeah, I wouldn't say it's all on Casper. You know, this is this limited set of high resolution 5-year hindcasts every other year. So we've got like maybe 20 start dates.
Can you let me know where it's stored?
Yeah, I can. soon. Judith.
In this context, I think it would be nice to do some of these, at least S2S runs. I was wondering if it makes sense for S2E or not, on variable resolution with refinement over CONUS, for example, and we should make sure it's big enough. I think some of the things that have been done on some of the grids are too localized, but I think we should maybe then go maybe into the ocean over the coastal regions and you know, talk to users and stuff. There would need to be one would need to do some work on how much you can actually go down in terms of variable resolution on what makes sense. But I would think the greater CONUS area for the typical CSM user.
Right. I mean, you're kind of getting into CESM3 world, right? Because we can't do that in CESM2 that I'm aware of.
Like you can't do coupled.
Well, can you do, you know, regional refinement and CAM in CESM2?
Yeah. Yeah, the regionally refined North Atlantic, we're doing the CSM2.
Okay.
But I don't know about coupled. I think Adam's just at the moment running some coupled simulations, but I don't think much has been done coupled.
I think I just talked to Brian Dobbins, so I think the MPAS variable resolution runs coupled as part of one of the CEMA demonstration projects. And this is the one which is too localized to make sense for more than one application, let's say. So I mean, the variable resolution does not extend in towards the West Coast or beyond the West Coast. But depending on which CEMA projects will get funded and go forward, there will be a version of that coupled, and it'll be based on CSM2 with MPAS variable resolution, CAM physics.
Yeah, I think that's a great idea, and it reminded me that I forgot to mention that we have this collaboration with Scripps doing, you know, redoing SMILE with high top CAM. So it kind of is along the same lines of first establishing your foundational hindcast set and then doing sensitivity studies of resolution, you know, initialization, etc. So we've kind of covered the atmospheric vertical resolution front, I think, and, you know, refined horizontal resolution, something that could build off of the current S2S or SMILE.
And I think there's plans to do this because I'm taken back how much. So depending on the science project, it might make sense or not to refine over CONUS. The other thing is to refine in the tropical belt. But I think there's a catalyst effort going on, but maybe more free running, I don't know, of refining over the ocean, in the tropics. And then the question is, do you get MJO teleconnections better, which would have applications for predictability.
Brian Medeiros is doing.
I think Brian is doing that, but I don't know the details, and I don't think it's initialized. Maybe Yaga knows, but she might be gone by now.
I think she's gone by now.
Yeah, I think you mean the regionally refined tropics. I think he's just running an F2000 case at the moment.
I think.
Yeah, I think I've seen some results by Lucas Harris initialized with MJO, and the MJO gets better in their case. And so I don't know if they looked into extratropical teleconnections, but that would be a potential for improved S2S forecasts.
I think Hyan's had her hand raised for a little while.
Oh. Go ahead, Hyan.
Oh, sorry, I already lowered my hand, but since Judith started the conversation about regional refined resolution, so Cascade and Hyperfast, these two DOE projects we're brainstorming right now to initialize E3SM regional refined model to produce some handcuffs for extreme events. This is an area that I think potentially Cascade can collaborate with Catalyst in the future too.
Great.
So one more thing real quick, I guess, is sort of changing topics. There is, DPLE has BGC variables, is that right?
Yeah.
Okay, again, I guess this goes to variables and we can have this conversation later, but something to consider as well for future efforts is maintaining BGC presence, because it's, we don't have a ton of observations to validate any of these forecasts, but we would have a better hope of doing so in like the S2S space more than the S2D space, because we don't have decades of BGC observations. We have like 10 years of BGC observations. So anyway, just something to consider as well.
Did you see Sam Mogan's talk?
Yeah, that's what I'm thinking of. Yeah, I didn't actually see his talk, but I have spoken to him about his work.
Yeah, I mean, it's true that the ocean has been sort of an afterthought in the S2S prediction experiments up to now. Certainly don't include BGC.
And I know that Shui Zheng's group in Washington, they also are interested in sort of more high frequency output in the upper ocean for air-sea interaction research.
What do you mean by high frequency? Daily?
Well, daily, so they are interested in salinity, and so they're having this model between, they're having in the observations, they're thinking that the MJO and so interactions, there's a large component where the precipitation freshens the water, and then that reacts with the Kelvin wave, and so they want daily upper ocean output. I have a list of variables they like. So for CSM3, we should involve them too.
I realize that this does nothing but present you with like problems. It just is more, you have to find more storage space and more compute time. Yeah, I guess I'm just trying to advocate for where we can't do research because we just simply don't have the data. That's all.
All right. I think things are winding down unless anyone has any final comments. If not, thanks everyone for participating, and hope to see everyone in June here at the annual workshop. Thanks everyone online.
Thank you. Bye, everyone.
Bye. Thanks, y'all. I love these things.